Imagine for a moment that you reach for a cup of coffee and your hand passes right through it, or you look up at the sky and instead of seeing familiar constellations, you watch as stars begin to wink out of existence, one by one. What if the ground beneath your feet simply stopped holding together and everything you've ever known began dissolving into chaos? This isn't a scene from a science fiction movie. It's a genuine scientific possibility that keeps physicists awake at night. We live in a universe governed by rules so reliable that we rarely stop to question them. Gravity keeps our feet on the ground, light allows us to see, and atoms hold together everything from the air we breathe to the cells in our bodies. But what if one of those fundamental laws of physics suddenly stopped working? What would happen to reality as we know it? Today, we're exploring one of the most profound and unsettling mysteries of the cosmos, a scenario known as the silent collapse. This is the idea that the very laws that hold our universe together could fail, either gradually or all at once, without warning and without any obvious cause. Unlike dramatic cosmic events like supernova or black hole collisions, a silent collapse might begin subtly, almost imperceptibly, like a single thread being pulled from a tapestry until the entire fabric of reality begins to unravel. From the disintegration of galaxies to the breakdown of time itself, the consequences would be both terrifying and fascinating, revealing just how fragile our understanding of the universe truly is. Join me on a journey into the heart of this mystery, where we'll confront questions that challenge everything we think we know about existence. What if gravity reversed? What if light refused to travel? What if the forces that bind atoms together simply let go? Together, we'll uncover why these laws are so essential, why they might not be as immutable as we assume, and what it would mean for humanity if the rules of the game suddenly changed. This is more than a theoretical exercise, it's a deep dive into the bedrock of reality itself, and by the end, you may never look at the world around you in quite the same way again. Think of the universe as the most intricate clockwork mechanism ever conceived, with every gear and spring perfectly aligned to keep time for billions of years. This cosmic clock doesn't run on magic or chance. It operates on a set of fundamental rules so consistent and reliable that we often forget they are even there. These are the laws of physics, the invisible architecture of everything. Gravity is the force that not only keeps your feet firmly on the ground, but also choreographs the majestic dance of planets around stars and galaxies around each other. Electromagnetism is the master weaver, binding atoms into molecules, allowing for the chemical reactions that power the sun and the intricate neural networks that power your thoughts. And thermodynamics governs the flow of energy itself, dictating why stars eventually burn out and why your morning coffee cools down if you leave it on the table. These principles are far more than abstract equations scribbled on a physicist's chalkboard. They are the very bedrock of reality, the foundational framework that makes existence possible. Without the strong nuclear force holding atomic nuclei together, every star in the sky would simply fizzle out into a cloud of subatomic particles. Without the precise value of the gravitational constant, the universe would either have expanded into a thin, lifeless mist or collapsed back on itself moments after the Big Bang. We assume these laws are constant, the same here on Earth as they are in the most distant galaxy we can observe, and the same today as they were 13.8 billion years ago. This assumption of constancy is the cornerstone of all scientific discovery and technological progress. It's why we can launch a probe to Pluto and know exactly where it will be years later, or why we can develop the silicon chips in your phone with the confidence that electrons will behave predictably. Our entire modern civilization is built upon this foundation of predictable physics. From the electricity lighting your room to the satellites enabling global communication, every technological marvel is a testament to our trust in these immutable rules. But this reliance invites a profound and somewhat unsettling question. What if that trust is misplaced? What if, somewhere in the vastness of space or the depths of time, a fundamental law begins to fray at the edges? The result wouldn't be a simple malfunction, it would be a descent into absolute chaos. Predictability would vanish into the void, and the intricate machine of the universe would, quite literally, fall apart at the seams. History offers us a fascinating and somewhat comforting pattern. Just when we think we have the universe completely figured out, it throws us a curveball that forces us to rewrite the textbooks. These moments of profound confusion, where the established laws of physics seem to falter, were not in points but rather the birth pangs of a deeper understanding. Consider the late 19th century. Physics was in many ways considered a finished science. The majestic edifice of Newtonian mechanics had successfully predicted the motions of planets and the fall of apples for over 200 years. Physicists like Lord Kelvin famously believed that all that remained was to measure things to a few more decimal places. But on the horizon, two tiny clouds were gathering that would soon unleash a storm of revolution. The first was the perplexing result of the Michelson-Morley experiment, which failed to detect the luminiferous ether, the supposed medium through which light waves traveled. This wasn't just a failed experiment, it was a direct challenge to the very foundation of classical physics, suggesting that the universe's rulebook was missing some crucial pages. The second cloud was the ultraviolet catastrophe, a problem where classical theory predicted that a hot object should radiate infinite energy at ultraviolet wavelengths, a result so absurd it was plainly wrong. These weren't mere puzzles, they were cracks in the bedrock of reality, and they led directly to the twin revolutions of relativity and quantum mechanics. Einstein's theory of relativity didn't just fix Newton's laws, it completely reimagined the nature of space, time, and gravity, showing that what we thought were immutable truths were actually just excellent approximations for the world we experience every day. This pattern of collapse and rebirth repeated itself decades later with the shocking discovery of dark energy. For much of the 20th century, the prevailing cosmological model involved a universe expanding from a Big Bang, but one that was gradually slowing down due to the relentless pull of gravity. That was until two teams of astronomers led by Saul Perlmutter and Adam Rees made an observation that sent shockwaves through the scientific community. By measuring the light from distant supernova, they found that the expansion of the universe wasn't slowing down at all, it was accelerating. This was as if you tossed a ball into the air and watched it not only defy gravity but shoot away faster and faster into the sky. This observation directly contradicted the expectations based on Einstein's own equations and the known contents of the universe. To make sense of it, physicists had to invoke a mysterious, repulsive force, dubbed dark energy, that makes up about 68% of the cosmos and whose nature remains one of the biggest unsolved mysteries in physics today. In each of these historical crises, the laws didn't truly break, they were revealed to be incomplete. A new, more encompassing theory emerged that could explain the old observations along with the new, bizarre ones. These paradigm shifts, as philosopher Thomas Kuhn called them, show that science progresses not by a steady accumulation of facts, but through these violent, transformative episodes where our entire worldview is overturned. Yet this history, while reassuring in its pattern of eventual resolution, contains a deeply unsettling seed of doubt. What if the next anomaly isn't resolved by a new theory? What if the next crack in the foundation isn't a crack at all, but the beginning of a true and permanent collapse? The crises of the past were like a temporary power outage. The lights flickered, we found a better generator, and everything came back on, brighter than before. The silent collapse we're discussing is the nightmare scenario where the power goes out for good, and there is no backup. It's the fear that one day, we might observe a galaxy rotating in a way that defies gravity, not because of dark matter, but because gravity itself is failing. Or we might measure a fundamental constant like the speed of light and find that it is genuinely, undeniably changing over time, with no deeper principle to explain why. This is the theoretical horror that haunts the edges of cosmology, the idea that the laws are not just approximations waiting for a better theory, but that they are truly local, temporary bylaws in a cosmos that can change its fundamental rules. It suggests a universe that is not ultimately comprehensible, where the bedrock of reality is, in fact, shifting sand. This silent collapse we've been exploring isn't a singular, explosive event that lights up the sky for all to see. It is something far more subtle and in many ways far more terrifying. Imagine the most vital, fundamental rule that governs our universe, the law of gravity, the constancy of the speed of light, the force that binds atoms simply ceasing to function. Not with a bang, but with a whisper. This failure could be instantaneous, a switch flipped somewhere in the cosmos, or it could be a slow, creeping decay over millennia, so gradual that its initial signs are dismissed as instrument error or statistical noise. There is no warning siren, no observable cause that our science could immediately pinpoint. It just begins, a silent and invisible unraveling of the very fabric of reality. Contrast this with the cosmic spectacles we often envision when we think of universal catastrophe. A supernova is a violent, brilliant death of a star, flooding its corner of the galaxy with light and radiation. A black hole collision sends literal ripples through the fabric of spacetime, disturbances we can now detect with incredibly sensitive instruments. These are dramatic, observable events. They follow rules we understand, even if their scale is immense. The silent collapse is the antithesis of this drama. Its insidious nature lies in its stealth. The first sign might be something seemingly minor and local. Perhaps a deep space probe begins reporting back data that is slightly, inexplicably off. Maybe the light from a distant quasar shows a frequency shift that cannot be explained by the Doppler effect. At first, these anomalies would be filed away as curiosities, puzzles for future scientists to solve. The true horror would only reveal itself as the effects begin to cascade. This is where the metaphor of a single thread being pulled from a vast and intricate tapestry becomes so powerfully apt. Our universe is not a collection of independent rules. It is a deeply interconnected web where each law supports and influences the others. The force of gravity shapes the large-scale structure of the universe, but it is electromagnetism that builds the atoms and molecules that form those structures. The nuclear forces that operate within an atom's heart are what provide the energy that allows stars to shine, creating the very elements that make up our world and our bodies. Tug on one thread, say, if the strong nuclear force were to weaken by even a fraction of a percent, and the unraveling begins, atomic nuclei would lose their cohesion. Stars would no longer be able to sustain fusion, their fires flickering out. Matter itself would become unstable. This initial failure would then pull on the next thread. Without stars, there is no light, no energy for life. Without stable atoms, there is no chemistry, no biology. The collapse would ripple outward from the quantum realm to the galactic scale, a total systemic breakdown initiated by a single, silent change to a fundamental constant. It is a domino effect where the first domino is the rulebook of existence itself, and the fall would be both absolute and, in its earliest stages, almost completely undetectable to those living within the tapestry. Now, let's bring this terrifying concept down to earth, quite literally, by examining the law we all think we know best, gravity. Picture Isaac Newton sitting under that apple tree, but instead of the fruit falling straight down and inspiring a law of universal gravitation, imagine it suddenly shooting upward into the sky, defying every expectation. This isn't just a whimsical thought experiment. It's a doorway into understanding how a single law's failure could unravel our entire existence. Gravity is the great organizer of the cosmos, the invisible hand that sculpts galaxies, keeps planets in their graceful orbits around stars, and gives weight to our world. Without its constant, reliable pull, the universe as we know it would not just change, it would cease to be coherent. The immediate consequences of gravity weakening or reversing would be both spectacular and apocalyptic. On the largest scales, the delicate celestial balance that has held for billions of years would instantly shatter. Planets would no longer be tethered to their stars. Earth would drift away from the sun, not in a slow spiral but in a catastrophic straight line into the freezing, dark void of interstellar space. The Moon would abandon its orbit around our planet, becoming just another rogue object hurtling through the solar system, but the chaos wouldn't stop there. Our own atmosphere, held in place by gravity, would simply begin to boil off into space. The air we breathe would vanish, not with a howling wind, but in a silent, deadly expansion as gases escaped into the vacuum. The very ground beneath our feet would offer no refuge. The structural integrity of everything from the mightiest mountain ranges to the steel and concrete of our tallest skyscrapers depends on gravity providing a constant downward force. If that force reversed, the concept of down would disappear. Buildings would be ripped from their foundations and flung upward, and the planet itself would begin to disintegrate, its rocks and soil no longer held together by their own weight. This scenario is not pure fantasy. It touches on the cutting edge of theoretical physics. Renowned physicist Lisa Randall of Harvard University has extensively explored the possibility that gravity, the weakest of the fundamental forces, might behave differently in other dimensions. In her work on warped geometries and extra dimensions, she theorizes that gravity's apparent weakness in our three-dimensional world could be because it is actually spilling into or being diluted by other spatial dimensions inaccessible to us. This isn't just mathematical speculation. It provides a plausible framework for how gravity's influence could fundamentally change. If a parameter in these higher dimensional models were to shift, the force we experience as gravity could weaken, strengthen, or even alter its attractive nature in our reality. This research, while aimed at unifying physics, inadvertently paints a picture of a universe where the rules are not fixed but are dependent on a cosmic architecture far more complex and potentially fragile than we ever imagined. Consider the real-world implications for something as seemingly straightforward as space travel. Our entire approach to launching rockets and navigating probes is a precise dance with gravity. We use its pull to slingshot spacecraft around planets for a speed boost, and we carefully calculate orbital mechanics, knowing that gravity will provide a constant, predictable curve. If that force became unpredictable, every satellite, from those providing GPS to those monitoring our climate, would immediately tumble out of control. The International Space Station would not just drift, it would be flung off on a chaotic trajectory. Future missions to Mars or beyond would become impossible, not due to a lack of engineering skill, but because the very map of the solar system would have been erased. Our daily lives are also deeply entangled with this force. The flow of rivers, the cycle of tides, even the way our cardiovascular system pumps blood against gravity's pull, all of it would be thrown into disarray. A world without reliable gravity is a world where the most basic physical expectations are betrayed. This leads us to a deeply unsettling and reflective question. In the face of such a fundamental betrayal, would humanity even have time to comprehend what was happening? The collapse would be so swift and so total that survival would be an impossible concept. There would be no time for scientific inquiry, no moment of collective realization. One instant, the universe would be operating under known rules. The next, it would be a chaotic soup of matter flying apart. The Earth itself, a beautiful and complex assembly of rock, metal, and water held together by gravity's embrace, would likely disintegrate into an expanding cloud of cosmic debris. Its story ended not with a slow cooling but with a sudden and silent dissolution. The silent collapse of gravity would be the ultimate demonstration of our profound vulnerability, a reminder that we exist at the mercy of laws we did not write and cannot control, living on a fragile world in a universe whose stability we must never take for granted. But if we shift our gaze from the force that binds the cosmos together to the very medium through which we perceive it, we encounter another pillar of reality so fundamental that its failure would unravel the fabric of spacetime itself. This pillar is the speed of light, denoted by the constant c in Einstein's famous equation. For over a century, we have understood that this value, 299,792,458 meters per second, is not just the speed at which light travels in a vacuum. It is the ultimate speed limit of the universe, the unbreakable rule governing causality, information, and the very sequence of events. It is the cosmic traffic law that prevents effects from happening before their causes, ensuring that the past remains the past and the future remains the future. To imagine this constant changing is to imagine the rulebook of reality being rewritten in the most chaotic way possible. Consider the profound implications if the speed of light were to suddenly increase. The most immediate and bizarre consequence would be a breakdown of causality, the principle that cause must always precede effect. With a higher speed limit for information, events that were once separated by a comfortable interval of time could suddenly become simultaneous or even reversed from certain perspectives. An explosion on a distant star might be seen from Earth almost instantly, but the sound, which travels much slower, could arrive before the light, creating a universe where you hear the bang before you see the flash. This isn't just a sensory oddity, it strikes at the heart of logic itself. Our entire understanding of physics, from the equations of motion to the laws of thermodynamics, is built on the unshakable assumption that the arrow of time points in one direction. If C changes, that arrow shatters. The past, present, and future would bleed into one another, creating a reality where history could be rewritten by events that haven't happened yet, a world where consequence loses all meaning. The technological collapse would be both swift and absolute. Our global society is precariously balanced on a foundation of precise timing, and that timing is entirely dependent on the constancy of light's speed. The Global Positioning System, or GPS, is a perfect example of our delicate dependence. Those satellites orbiting high above the Earth don't just broadcast their location, they broadcast the exact time down to a fraction of a nanosecond. Your phone or car's GPS receiver calculates its position by measuring the tiny delay in how long those time signals take to arrive, a calculation that requires knowing the speed of light with incredible precision. But if C were to change even slightly, the entire system would instantly fail. The calculations would be wrong. Your navigation app might tell you you're in the middle of the ocean when you're actually sitting in your living room. Beyond the inconvenience of lost directions, this would ground airplanes, disable financial networks that rely on time-stamped transactions, and halt shipping logistics worldwide. The silent, invisible thread of light speed that synchronizes our modern world would have been cut. This concept is far from pure science fiction. It lives in the fringes of legitimate cosmological debate. Albert Einstein himself, the architect of this constant's prominence, expressed a deep concern late in his life. He wondered if the fundamental constants of nature, including the speed of light, might actually be variables that change imperceptibly slowly over cosmic time. This idea, now known as the varying constants hypothesis, is actively investigated by cosmologists today. By studying the light from incredibly distant quasars, ancient beacons whose light has been traveling for billions of years, scientists like John Webb and his team have analyzed the fine structure constant, a number that incorporates the speed of light. Their controversial findings suggest this constant might have been slightly different in the early universe. While these results are hotly debated and far from conclusive, they open a terrifying door to the possibility that the laws of physics are not set in stone but are more like local ordinances, subject to change over astronomical timescales or across vast distances. It suggests that the silent collapse could be a slow, cosmic drift rather than a sudden snap. The most personal and philosophical consequence of a changing sea would be the complete erosion of our shared reality. We experience the universe through the information carried to us by light and other electromagnetic waves. The starry night sky is a mosaic of the past. We see stars not as they are now, but as they were years, centuries, or millennia ago. This delay is built into our perception of the cosmos. If the speed of light were no longer constant, this historical record would become distorted and unreliable. The comforting idea of a universal now would vanish. Two people standing next to each other could potentially perceive events in a different order if the light from those events arrived at unpredictable speeds. Your past could be someone else's future, dissolving the common timeline that allows us to agree on history, share experiences, and build a coherent society. The very concept of truth, based on observable and verifiable events, would become fluid and subjective, leaving us isolated in our own personal, and now unshareable, realities. While gravity orchestrates the grand ballet of the cosmos and the speed of light defines the very stage of spacetime, there is a force that operates on a more intimate, yet equally vital, scale of force that literally holds you and the world around you together. This is electromagnetism, the master builder of reality. It is the invisible glue that binds atoms into the molecules that form the water you drink, the air you breathe, and the DNA that encodes your very existence. It is the force behind every chemical reaction, from the fiery fusion in the heart of a star to the subtle neural impulses that form a single thought in your mind. Without the elegant dance of attraction and repulsion between positively charged protons and negatively charged electrons, matter as we know it would simply not exist. There would be no solidity, no structure, no complexity, just a formless, chaotic sea of disconnected particles. To understand the sheer elegance of this force, one need only turn to the legendary physicist Richard Feynman. In his famous lectures, he didn't just explain electromagnetism, he marveled at it. He described it as the force that makes it possible for you to push your hand through a table, not because your hand is solid, but because the electromagnetic fields of the atoms in your hand are repelling the electromagnetic fields of the atoms in the table with incredible strength. This force is what gives matter its illusion of solidity. It dictates how atoms link arms to form molecules, how those molecules interact to create everything from simple water to the incredibly complex proteins that form the machinery of life. Feynman famously stated that if he had to convey the most important scientific knowledge to future generations in a single sentence, it would be that all things are made of atoms and that their behavior is governed by the electromagnetic force. Its failure would therefore mean more than just a change in the rules. It would mean the complete and utter erasure of the game itself. Now, imagine the silent collapse begins here. The electromagnetic force doesn't vanish with a dramatic flash. It simply begins to fade, like a light on a dimmer switch being slowly turned down. The first thing you might notice is the light literally vanishing from the world. Light itself is a propagating wave in the electromagnetic field. As the force weakens, photons lose their energy and their ability to travel. The sun would still be a massive ball of fusion in the sky, but its light would never reach your eyes. The world would plunge into an absolute, impenetrable darkness, deeper than any cave, because even artificial lights would be unable to function. But the darkness would be the least of your worries. As the force continues to wane, the very bonds holding your world together would start to dissolve. Consider the simple, everyday action of flipping a light switch. Your finger moves to toggle the switch, expecting to complete a circuit and allow electrons to flow. But in a world where electromagnetism is failing, that expectation is betrayed. The electrons in the wires, once compelled to move in an orderly fashion by electromagnetic fields, now have no reason to respond. The switch flips, but nothing happens. No current flows, no light appears. This failure would ripple out instantly to every piece of technology you rely on. Your phone becomes a lifeless slab of glass and metal. The Internet, a global network built on electromagnetic signals traveling through wires and fiber optics, goes silent. Every motor, every computer, every device that defines modern civilization would cease to function, not because they are broken, but because the fundamental principle that allows them to operate has been revoked. This technological blackout, however, is merely a prelude to the true horror. As the force weakens further, atomic bonds begin to fail. The molecules that make up the air around you would drift apart, turning the atmosphere into a thin, unbreathable mist of separate atoms. The solid ground beneath your feet would lose its integrity, its atoms no longer clinging together. You would witness the world around you, the buildings, the trees, your own body beginning to sublimate into a diffuse cloud of particles. There would be no explosion, no dramatic crumbling. It would be a silent, terrifying dissipation, a return to a primordial state of disconnected matter. Life itself, a phenomenon entirely dependent on exquisitely precise electromagnetic interactions within and between cells, would be instantly and irrevocably extinguished. Your neurons could no longer fire, your heart could no longer beat. The enzymes that catalyze the reactions keeping you alive would fail to recognize their targets. Every living cell in every plant, animal, and person would simply cease to function, dissolving along with the rest of the physical world. The catastrophe would not be confined to our pale blue dot. Out in the cosmos, stars are also slaves to electromagnetism. The intense heat and pressure in their cores force atomic nuclei together in the process of fusion, but it is the electromagnetic force that the nuclei must overcome to fuse. If electromagnetism were to change, the delicate balance of stellar physics would be destroyed. Stars might explode in a final, furious release of energy, or they might simply gutter out like candles in a vacuum, plunging the universe into a cold, dark, and lifeless silence. The failure of electromagnetism is the ultimate unraveling, a collapse that doesn't just destroy structures but annihilates the very possibility of structure, leaving behind a cosmos that is empty, dark, and utterly, profoundly meaningless. Yet, even as we grapple with the silent dissolution of matter and energy, we must confront a law that is perhaps even more fundamental to our experience of reality, a principle that dictates not just how things change, but the very direction of change itself. This is the second law of thermodynamics, and it presents us with a concept that feels almost philosophical in its weight: entropy. In simple terms, entropy is a measure of disorder, of the universe's relentless slide from neat, organized states towards ever greater chaos and randomness. The second law states that the total entropy of any isolated system can never decrease over time. It's the reason why a drop of ink diffuses throughout a glass of water, but never spontaneously reforms into a single, concentrated droplet. It's why a hot cup of coffee will always cool down to room temperature, its heat energy dispersing into the surrounding air, and why that same energy will never spontaneously gather back into the cup to reheat it. This inexorable increase in disorder is what physicists call the arrow of time. It gives us a past that is distinct from the future, a timeline where events progress in one irreversible direction from order to chaos. Now, let's imagine the silent collapse strikes here at the heart of this universal principle. Picture a world where entropy doesn't increase but begins to decrease. The consequences would be so bizarre that they would unravel the very fabric of causality and memory. Heat would no longer flow from hot objects to cold ones. Instead, you'd witness frost forming on a boiling kettle as warmth fled from the water and into the colder air. A shattered vase would not lie in pieces on the floor. The fragments would suddenly leap up from the ground, reassembling themselves perfectly on the table without a single crack. But the true psychological terror would unfold within our own minds. Our memories are stored as orderly arrangements of neural connections, formed by the increase of entropy in the broader universe that allowed those specific brain states to occur. If entropy were to reverse, so too would the process of memory formation and recall. You might find yourself vividly remembering events from tomorrow while completely forgetting what you had for breakfast this morning. Your sense of a continuous self, built upon a linear progression of experiences from birth to the present moment, would shatter into a confusing jumble of disconnected and potentially prophetic moments. The past and future would lose all meaning, leaving you trapped in a perpetual, disorienting present where effect precedes cause, and the world is literally falling into order. To truly appreciate the profound weirdness of a reversed arrow of time, we can turn to a famous thought experiment conceived by the physicist James Clerk Maxwell in the 1860s. He imagined a tiny, mischievous being later dubbed Maxwell's demon guarding a small door between two chambers of gas. This demon could see individual molecules and would only open the door to let fast-moving, hot molecules into one chamber and slow-moving, cold molecules into the other. Without expending any energy itself, the demon would be able to violate the second law by creating order from disorder. One chamber would become hot and the other cold, effectively decreasing the overall entropy of the system. For over a century, this paradox plagued physicists. It wasn't until the 20th century, with the development of information theory, that a resolution was found. Scientists like Leon Brillouin and Charles Bennett argued that the demon isn't free. To see the molecules, it must gather information about them, and the process of acquiring and erasing that information itself requires energy and increases entropy elsewhere in the system. The demon, in trying to create a local pocket of order, inevitably creates a greater amount of disorder in its own operational process, thus preserving the second law. But in our scenario of silent collapse, this safeguard fails. The fundamental link between information, energy, and entropy is broken. Maxwell's demon wouldn't just be a thought experiment. It would become a reality, not through cunning engineering, but because the universe itself had ceased to enforce its most basic rule about the flow of time. Theoretical physicist and author Sean Carroll has spent much of his career exploring this deep and mysterious connection between entropy and time. He often explains that the reason we remember the past and not the future is not because of some intrinsic property of time itself, but purely because the past was a state of lower entropy. The entire universe began in an incredibly ordered, low entropy state, the Big Bang, and has been evolving towards higher entropy ever since. This gradient, this difference between the past order and future disorder, is what creates the arrow of time we all experience. Carroll poetically states that we are self-aware pieces of the universe who have emerged from this low entropy past, and our perception of time's flow is a direct consequence of that journey. If entropy were to decrease, this beautiful and coherent narrative would collapse. The universe would be moving backwards in time from our perspective towards its own beginning. We would experience the future as a state of increasing order and the past as one of increasing chaos, a complete inversion of everything that feels natural and real. Our entire existence is a story written on the sloping hillside of increasing entropy, and if that hill were to suddenly flatten or tilt in the opposite direction, the story would not just end, it would be read backwards, its plotlines unraveling into incomprehensible nonsense. This invites a moment of profound personal reflection. Every single day, you make thousands of assumptions based on the unwavering truth of the second law. You trust that your memories of yesterday are a reliable record of what actually happened. You expect that the food you cook will heat up and not suddenly freeze. You believe that as you grow older, you accumulate experiences, building a life that moves forward in a logical, linear progression. All of this, every ounce of your understanding of cause and effect, relies entirely on the silent, unseen increase of entropy in the universe around you. It is the most fundamental backdrop to your consciousness, a law so deeply ingrained in reality that its failure is almost unthinkable. A silent collapse of thermodynamics would be more than a physical catastrophe. It would be an epistemological one, destroying the very basis of knowledge and experience. It asks us to consider what is truly real, the solid objects around us, or the invisible, irreversible flow of time that gives those objects their history and their future. But now, let's leave the familiar world of large-scale forces and descend into the bizarre and counterintuitive realm of the very small, where the rules of the game are written not in certainty, but in probability. This is the domain of quantum mechanics, a theory so successful and yet so strange that even its founders argued over what it truly meant. At its heart lies a principle that feels almost philosophical, Heisenberg's uncertainty principle. It tells us that there is a fundamental limit to what we can know about a particle. We cannot pin down both its exact position and its exact momentum at the same time. The more precisely we measure one, the more fuzzy and uncertain the other becomes. This isn't a limitation of our instruments. It is a fundamental property of the universe itself. Reality at its most basic level is not a collection of definite things, but a cloud of probabilities and potentialities. An electron doesn't exist in one place orbiting a nucleus. It exists in a haze of possible locations, a superposition of states, only settling into a definite position when we force it to by making a measurement. Imagine if this foundational principle, this inherent uncertainty, were to suddenly fail. The silent collapse here would not bring chaos, but a chilling, absolute certainty. The quantum world would become predictable. We could, in theory, know the exact trajectory of every electron, the precise state of every particle. On the surface, this might sound like a physicist's dream, the ultimate triumph of determinism, a universe finally stripped of its quantum weirdness. But this victory would be a Pyrrhic one, achieved at the cost of reality itself. The first casualty would be the very structure of matter. Atoms are stable because of the uncertainty principle. An electron confined to the tiny space around a nucleus must, according to quantum rules, have a certain minimum amount of energy or motion. If we could know its position with absolute certainty, that would imply it had zero momentum, which would violate this rule. Without this quantum jitter, this fundamental uncertainty, electrons would spiral catastrophically into the nucleus, and every atom in the universe would instantly collapse. All matter would implode into a dense, featureless pulp in a fraction of a second. This catastrophic chain reaction finds a famous, if gruesome, analogy in Schrödinger's cat paradox. Erwin Schrödinger devised this thought experiment not to explain quantum mechanics, but to highlight what he saw as its absurdity when applied to the everyday world. He imagined a cat in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter triggers the hammer to break the vial, killing the cat. According to quantum rules, the radioactive atom exists in a superposition. It has both decayed and not decayed until someone opens the box and observes it. Therefore, by extension, the cat must also be in a superposition, both alive and dead simultaneously, a blur of two possibilities. We understand this today not as a literal undead cat, but as a mathematical description of the probability wave linking the atom's state to the cat's fate. Now picture a silent collapse that resolves this superposition not through observation but by fiat. The quantum probability wave wouldn't just collapse, it would snap, forcing a single, definite outcome everywhere at once. In our macroscale world, this might manifest as objects flickering between states. A chair might momentarily cease to be solid as the atoms in it briefly lose their defining properties. Living things could find their biological processes, which rely on quantum effects in enzyme reactions and photosynthesis, suddenly and fatally disrupted. The quantum weirdness that was once confined to the lab would erupt into our daily lives with disastrous consequences. This potential for a quantum collapse forces us to confront a deep and ongoing debate among physicists. Are the laws of quantum mechanics truly universal, or are they just an approximation, a local set of rules that might not hold everywhere in the cosmos? The pioneers of the field were deeply troubled by this. Werner Heisenberg, who formulated the uncertainty principle, saw it as a fundamental limit on knowledge, not just a technical hurdle. Modern researchers continue to probe this question. Some theories, like spontaneous collapse models, propose that there is a mechanism so far undetected that prevents superpositions from persisting for too long or at too large a scale. Others, working on theories of quantum gravity, wonder if the extreme conditions near a black hole singularity or at the moment of the Big Bang might temporarily suspend or alter quantum rules. The terrifying implication of this research is that the quantum laws we take for granted might not be the final word. They could be subject to change, to failure, or to regional variation, making our universe far less stable than it appears. This leaves us with a profound and deeply personal question. If faced with a choice, would we prefer a quantum world governed by uncertainty or a deterministic one governed by certainty? The uncertain quantum world can feel unsettling. It tells us that at its core, reality is probabilistic, not mechanical. There is an element of chance, of fundamental unpredictability. Yet, as we've seen, this very uncertainty is the glue that holds atoms together and enables the technologies of the future, like quantum computing. A certain, deterministic quantum world might seem more comforting on the surface, a universe where everything is knowable and predictable. But as we've explored, that certainty is a phantom. It is the certainty of a clockwork universe that has broken its mainspring. a predictable path that leads only to collapse and silence. The beautiful, maddening uncertainty of the quantum realm is not a flaw. It is the feature that allows for complexity, for life, and for a universe rich with possibility. Its failure would not bring order, but the most profound and absolute chaos imaginable. While the forces we've explored so far shape the world at a grand scale, there is an even more fundamental power operating in the heart of every atom, a force so potent that it literally holds the fabric of reality together. This is the strong nuclear force, nature's ultimate superglue. Imagine the nucleus of an atom, a tiny cluster of positively charged protons and neutral neutrons packed together unimaginably tightly. According to the rules of electromagnetism, those positively charged protons should violently repel each other, blowing every atomic nucleus apart in a fraction of a second. But they don't. Something far stronger overwhelms that electromagnetic repulsion, binding the nucleus together with an iron grip. This is the strong force, the mightiest of the four fundamental forces of nature, but with the shortest range, acting only within the confines of the atomic nucleus. It is the reason matter has substance and stability. Without it, the universe would be nothing but a diffuse, expanding cloud of hydrogen atoms, unable to form the elements that build stars, planets, and life itself. Now, let's envision the silent collapse beginning here with this most essential of forces. The strong nuclear force doesn't vanish with a thunderclap. It simply begins to weaken, like a powerful adhesive slowly losing its potency. The immediate effect would be a quiet, universal decay starting at the smallest possible scale. Atomic nuclei, no longer held together by that immense binding energy, would begin to fly apart. This wouldn't be a chemical reaction or a simple breakdown. It would be the very definition of matter coming undone at the seams. Every object around you, once composed of stable elements, would suddenly become intensely radioactive as atoms spontaneously fission, releasing torrents of energy and subatomic particles. The air you breathe, mostly nitrogen and oxygen, would begin to disintegrate, transforming from a life-giving gas into a lethal bath of radiation. The ground beneath your feet would cease to be solid, its atomic structure dissolving into a vaporous, energetic mist. In a world where the strong force fails, there is no such thing as stable matter anymore. The most terrifying aspect of this collapse is its intimacy. This isn't a disaster happening out in the cosmos. It is a dissolution happening to you, personally and inescapably. Your own body is a collection of trillions of atoms, all held together by the relentless, unwavering strength of the strong nuclear force. If that force weakens, the atoms in your cells begin to come apart. There is no pain, no dramatic sensation, only a quiet and horrifying unraveling. The molecules that form your DNA, your proteins, your very bones and flesh would simply dissipate. You would not crumble to dust. You would slowly and silently fizzle apart, your body dissolving into a cloud of elementary particles and energy. It is a fate beyond any conventional understanding of death, a return to the primordial state of the universe before atoms could even exist. This catastrophic unraveling finds a powerful analogy in the simple image of glue losing its stickiness. Think of the protons and neutrons in a nucleus as being coated in an incredibly powerful, specialized glue, the strong force. This glue is so effective that it can easily overcome the natural tendency of the protons to push each other away. Now, imagine that glue suddenly becoming watery and weak. The components it was holding together wouldn't just slowly separate. They would explode outward, driven apart by the pent-up repulsive energy that the glue was once containing. This is precisely what would happen inside every single atomic nucleus in the universe. The binding energy that was stored there would be released in a catastrophic instant, a silent, universe-wide explosion happening at the quantum level. Our understanding of this incredible force comes from humanity's most ambitious experiments, the massive particle accelerators like the Large Hadron Collider. These colossal machines are essentially microscopes for the universe, smashing particles together at velocities approaching the speed of light to recreate the conditions of the early cosmos. In the fleeting, fiery moments after these collisions, for a fraction of a heartbeat, we can glimpse the strong force in its pure, unadulterated state, the same state it was in just moments after the Big Bang. Physicists probe these limits to understand the rules that govern quarks and gluons, the fundamental particles that mediate the strong interaction. These experiments have confirmed the force's immense power and its critical role, but they also subtly highlight its potential fragility. They show us that the stability we take for granted is dependent on a perfect, and perhaps precarious, balance of constants. Tweak one underlying parameter, and the entire elegant structure could, in theory, come tumbling down. The repercussions would echo from the quantum realm to the cosmic scale. Out in the universe, stars are the great furnaces where the strong force is put to work. Through the process of nuclear fusion, the intense heat and pressure in a star's core force atomic nuclei together, overcoming their electromagnetic repulsion. The strong force then takes over, binding them into new, heavier elements and releasing the energy that makes stars shine. If the strong force weakens, this process grinds to a halt. Stars can no longer fuse hydrogen into helium. Their fires would gutter out, not in a supernova explosion, but in a slow and cold dimming. The cosmos would be plunged into an eternal, deepening night as the lights of the universe, one by one, go out forever. The silent collapse of the strong nuclear force is the ultimate undoing, a failure that doesn't just destroy the universe's contents, but rewinds its very evolution back to a time before atoms, before stars, and before any hope of complexity or life. While the strong force acts as the unbreakable glue holding atomic nuclei together, there is another, more subtle nuclear force working behind the scenes, a cosmic alchemist that tirelessly reshapes the very elements of existence. This is the weak nuclear force, and its domain is the mysterious process of radioactive decay. Unlike the mighty strong force, the weak force is, as its name implies, comparatively feeble and operates over an even shorter range. But its subtle power is unparalleled in its purpose. It is the master of transformation, the force that allows one type of subatomic particle to literally change into another. It is the reason some atomic nuclei are unstable, eventually shedding particles and energy to become a different element entirely. This process of radioactive decay is not just a curiosity. It is the heart of the nuclear furnace within stars and the very reason you and everything you see around you exists at all. The weak force's most crucial role is as the primary engine of stellar nucleosynthesis, the creation of new elements inside stars. In the unimaginable heat and pressure of a star's core, the main event is the fusion of hydrogen into helium, a process powered by the strong force. But to build anything heavier like the carbon in your body or the oxygen you breathe, the star needs a more sophisticated toolkit. This is where the weak force takes center stage. It enables a crucial step called the triple alpha process, where 3 helium nuclei are fused into a single carbon nucleus. This process relies on a specific type of radioactive decay mediated by the weak force to work efficiently. Without this delicate nuclear manipulation, the process would be far too slow, and the universe would be starved of carbon, the fundamental building block of life as we know it. The weak force continues its work in the final, spectacular moments of a massive star's life. During a supernova explosion, the intense flood of neutrinos elementary particles that only interact via the weak force, triggers a frantic series of reactions that forge the heavy elements, from the iron in your blood to the gold in a wedding ring, and flings them out across the cosmos. Now, let's subject this delicate alchemist to the silent collapse. Imagine the weak nuclear force begins to fail. The consequences would not be as instantly violent as the disintegration caused by the strong force's failure, but they would be equally absolute in their finality, playing out on a cosmological timescale that would leave the universe barren and inert. The most immediate effect would be a profound alteration in the rate of radioactive decay. Depending on the nature of the failure, these decay processes could either screech to a halt or accelerate into a frenzied, chaotic rush. If decay rates were to slow or stop, the radioactive elements that heat our planet's core would cease their gentle, steady release of energy. Earth's magnetic field, which is generated by the churning of our molten iron core and protects us from harmful solar radiation, would begin to weaken and eventually vanish. Our atmosphere would be stripped away by the solar wind, and the planet would become a cold, lifeless rock exposed to the full fury of space. This intimate connection between nuclear physics and planetary habitability was something the brilliant astrophysicist Subrahmanyan Chandrasekhar understood deeply. His groundbreaking work on stellar structure and evolution revealed the exquisite balance of forces inside stars. He showed how the life cycle of a star, from its birth in a cloud of gas to its death as a white dwarf, neutron star, or black hole, is a precise dance governed by these fundamental interactions. A failure of the weak force would break this dance mid-step. Chandrasekhar's calculations detailed how stars rely on a sequence of nuclear reactions, each building on the last to progress through their evolution. If the weak force failed, that progression would freeze. Stars would become stuck, unable to move beyond burning hydrogen into helium. They would never become the red giants that create carbon, nor would they ever explode as supernova to seed the galaxy with the elements of planets and life. The universe would be filled with immortal, juvenile stars, shining with a dull consistency but incapable of creating anything new or complex. The most devastating illustration of this collapse can be found in the catastrophic failure of a supernova. In a healthy, functioning universe, a supernova is the ultimate act of cosmic recycling. The collapse of a massive star's core creates unimaginable densities and temperatures, and a blast of neutrinos particles governed by the weak force triggers a shockwave that both destroys the star and creates the periodic table's heaviest elements. This material is then blasted across interstellar space, eventually coalescing into new solar systems rich with a variety of elements. Now, picture this process gone horribly wrong. In a universe where the weak force has failed, the supernova's crucial final act is cancelled. The neutrinos cannot mediate the reactions necessary to forge heavy elements. The explosion might still occur due to gravity, but it would be a sterile event, a mere dissipation of energy. No gold, no uranium, no iodine would be created. The stellar debris would consist only of the lighter elements like hydrogen and helium, the primordial ashes of the Big Bang. Without the products of supernova nucleosynthesis, there could be no rocky planets like Earth, no mineral diversity, no chemical complexity that could ever give rise to life. The cosmos would be condemned to eternal simplicity, a vast and empty expanse of gas and dim stars, its potential for wonder and complexity forever extinguished by the silent failure of its most subtle craftsmen. Yet for all its proven robustness, the world of theoretical physics is never completely silent, and there are whispers from the fringe that suggest even relativity's reign might not be absolute. Cosmologists like Joe Megiddo have proposed controversial ideas such as variable speed of light cosmology, a theory that suggests the constant c might not have been so constant in the very early universe. While these ideas remain highly speculative and far outside the scientific mainstream, they serve a vital purpose. They remind us that our understanding, no matter how well tested, is a model of reality, not reality itself. They force us to confront the humbling possibility that our most cherished theories might be approximations, waiting for a deeper, more encompassing framework to come along. This isn't to say relativity is wrong, but that its absolute dominion might have limits we haven't yet discovered, boundaries beyond which space-time itself might behave in ways that would seem, to us, like pure magic or utter chaos. This entire discussion leads to a moment of quiet, personal reflection on the invisible architecture of our daily lives. We live in a world utterly dependent on the precision of Einstein's theories, yet we almost never stop to appreciate it. The satellite that beams your favorite show to your television is orbiting 12,000 miles above the Earth, where gravity is weaker and time ticks fractionally faster than it does on the surface. If the onboard computer did not constantly correct for this relativistic time dilation, its internal clock would drift and its positional data would become useless within minutes. The entire system would fail. The same is true for the networks that facilitate global financial trading, where nanosecond precision is mandatory, and for the atomic clocks that define the very second we all live by. Our entire technological civilization is, in a very real sense, built upon a 100-year-old theory conceived by a patent clerk in Switzerland. We are threading the needle of reality using a map drawn by relativity, and we trust implicitly that the map is accurate. The silent collapse of these relations would be more than a scientific curiosity. It would be the immediate and total failure of the global nervous system, a return to a disconnected, disoriented world where the shared, precise understanding of where we are and when we are would dissolve into a chaos of conflicting, broken signals. And now we arrive at one of the most profound and mysterious forces in all of cosmology, a phenomenon so enigmatic that it makes up nearly 70% of the entire universe, yet we understand almost nothing about it. This is dark energy, and its primary representative in our equations is a term known as the cosmological constant. First introduced by Einstein as a fudge factor to keep his static universe model from collapsing under its own gravity, the cosmological constant was later resurrected with a vengeance when astronomers made a discovery that would turn cosmology on its head. We now understand this constant not as a mistake, but as the best description we have for the repulsive force causing the expansion of the universe to accelerate, pushing galaxies apart from one another at an ever-increasing rate. It is the anti-gravity, the vacuum energy woven into the very fabric of spacetime itself, relentlessly driving the cosmos apart. The potential for a silent collapse here is uniquely terrifying because it wouldn't just change the universe, it would rewrite its ultimate destiny. For decades, cosmologists debated the final fate of the cosmos. Would it expand forever in a slow, cold fade known as the heat death, or would gravity eventually win, pulling everything back together in a fiery cataclysm called the Big Crunch? The discovery of dark energy and the accelerating expansion seemed to settle the argument firmly in favor of an eternal, ever faster expansion. But what if the cosmological constant, the driver of this acceleration, is not so constant after all? If this value were to vary, to weaken or vanish entirely, the consequences would be as dramatic as they are absolute. The relentless push of dark energy would cease. The expansion of the universe, which has been speeding up for billions of years, would suddenly slam on the brakes. Without this repulsive force to counter it, gravity would once again become the dominant player on the cosmic stage. The expansion could halt altogether, hanging in a precarious balance for a fleeting moment before reversing course. Galaxies would begin moving toward each other, their light blue shifting as they approach. The universe would start to contract slowly at first, then with increasing speed, temperatures rising as all matter and energy are compressed into an ever smaller volume, culminating in the ultimate Big Crunch, a fiery, singular end to everything. Alternatively, if the constant were to strengthen unpredictably, the acceleration could become so violent that it would overcome not just gravity, but every other force holding matter together. This scenario, known as the Big Rip, would see galaxies, stars, planets, and even atoms themselves torn apart by the runaway expansion of space itself. The silent collapse of the cosmological constant isn't just the failure of a law, it is the failure of the universe's very fate. This isn't just theoretical doom-mongering, it is an active and heated debate at the highest levels of cosmology. Nobel laureate Adam Rees, one of the key astronomers who discovered the accelerating expansion, is now at the forefront of efforts to determine whether dark energy is truly constant. His team uses the Hubble Space Telescope and other observatories to meticulously measure the light from distant supernova and quasars, looking for tiny variations in the expansion rate over cosmic time. They are essentially taking the universe's pulse, searching for any sign that the force we call the cosmological constant might be changing, however subtly. The data is incredibly challenging to interpret, and the uncertainties are vast, but the mere possibility is what fuels the debate. Other cosmologists propose that dark energy isn't a constant at all, but a dynamic field they call quintessence, which could evolve and change over billions of years. The silent collapse might not be a sudden off switch, but a slow, cosmic drift in the properties of this field, a gradual shift in the rules that would forever alter the trajectory of everything that exists. To truly grasp the scale of this force, we can look to the observational evidence that revealed it. When astronomers look out at distant galaxies, they use a phenomenon called redshift. As the universe expands, the light waves from these receding galaxies are stretched, shifting their color toward the red end of the spectrum. The farther away the galaxy, the greater the redshift, telling us how fast it is moving away from us. The shocking discovery in the late 1990s was that the light from the most distant supernova was less redshifted than it should have been if the universe's expansion were slowing down. This meant that these immensely far-off galaxies were not being slowed by gravity, they were accelerating away from us. It was as if you tossed a ball into the air, and instead of it slowing down and falling back, it shot away from your hand faster and faster into the sky. This observation, confirmed again and again, is the direct fingerprint of dark energy's work. It is the visible proof of a force acting on a cosmic scale, a force that determines whether galaxies will continue to flee from one another into an ever lonelier future, or whether they will one day turn around and begin a long, fatal journey back toward each other. This brings us to the ultimate, haunting question about a silent collapse in this domain. If the cosmological constant were to fail, would it simply mean the end of all galaxies in a violent Big Crunch or a cold, lonely stagnation? Or could it potentially give rise to an entirely new type of universe emerging from the ashes of the old? Some speculative theories suggest that a change in this fundamental constant could trigger a phase transition in the vacuum of space itself, a shift to a new state with completely different physical laws. In this scenario, the collapse of our familiar dark energy wouldn't be an end, but a transformation, a cosmic rebirth into a new reality with its own unique constants and forces, a universe utterly alien and incomprehensible to us. It forces us to confront the possibility that our entire cosmos, with its specific set of rules that allow for our existence, might be just one temporary configuration in a much larger, much stranger multiverse where the silent collapse of a constant is not a catastrophe, but simply the turning of a page. But if the bedrock of our own dimension proves unstable, could there be a safety net woven from the fabric of reality itself, a theoretical framework where the rules are not universal but merely local? This is the profound promise and profound peril of string theory, a candidate for the long-sought theory of everything that radically reimagines the cosmos not as a universe but as a multiverse. In this view, the fundamental laws of physics we hold so dear, the strength of gravity, the mass of an electron, the value of the cosmological constant, are not absolute, unchanging truths etched into the cosmos. They are instead more like local weather patterns, variable conditions that can differ from one region of reality to another. String theory proposes that at the most fundamental level, everything is composed of unimaginably tiny, vibrating loops of energy called strings. The way these strings vibrate determines the properties of the particles they manifest, from quarks to photons. But for the mathematics of these vibrations to work, they require more room to resonate than our familiar 3 dimensions of space and 1 of time. String theory demands extra dimensions, as many as 6 or 7 additional spatial dimensions curled up into shapes so small we cannot perceive them. This is where the concept of a safety net emerges. If these extra dimensions exist, and if the laws of physics are ultimately determined by the geometry of these hidden spaces, then a silent collapse in our 4-dimensional realm might not be a universal apocalypse. It could be a localized disaster contained within our particular membrane of reality. Theorists like Brian Greene, a leading proponent and eloquent communicator of string theory, often speak of this framework with a sense of awe at its mathematical elegance and its potential to unify all forces of nature under one beautiful, overarching principle. He describes a multiverse landscape, a vast cosmic ocean where each universe is like a separate bubble or a membrane, often called a brain, floating within a higher dimensional bulk. Each of these brains could have its own unique set of physical laws, determined by the specific way its extra dimensions are curled and folded. In this breathtaking vista, a catastrophic change in the laws governing our brain might be tragic for us, but it would be merely a local event in an unimaginably vast and varied multiverse. Life and complexity could thrive utterly untouched in a neighboring brain just a millimeter away in a higher dimension, separated from our catastrophe by a gulf we cannot cross. Yet for every promise of refuge, there is an equal and opposite risk of vulnerability. This multiverse ocean is not necessarily a calm and separated collection of ponds. It could be a turbulent sea where events in one brain can catastrophically affect another. The same higher dimensional bulk that isolates us could also serve as a conduit for disaster. Imagine our universe as a ship sailing on this ocean. A silent collapse might not be like our ship simply sinking in isolation. It could be like our hull springing a catastrophic leak, and that leak beginning to flood not just our ship, but the entire flotilla of nearby universes through the connecting medium of the bulk. A cascading failure of physical laws could, in theory, jump the gap between dimensions, turning a local tragedy into a regional or even multiversal catastrophe. The very interconnectedness that makes string theory so elegant could also be its greatest weakness, creating a chain of existential vulnerability that stretches across the cosmos. This forces us to a deeply philosophical crossroads. When we contemplate the silent collapse of a physical law, are other dimensions our ultimate refuge, a guarantee that something will persist even if we are lost? Or do they represent an even greater source of vulnerability, exposing us to threats and failures from realms we cannot even perceive? The mathematics of string theory is so complex and the ideas so speculative that they currently lie beyond the reach of experimental verification. They represent a magnificent, breathtaking possibility, a vision of reality far grander and more strange than we ever imagined, but they do not yet offer comfort. They simply expand the scale of the question, transforming our fear of a silent collapse from a concern for our universe into an awe-inspiring contemplation of a multiverse whose true rules, stability, and ultimate nature remain the greatest of all cosmic mysteries. But as we grapple with the terrifying possibility of a silent collapse, we are inevitably drawn to a profound and almost mystical question. Why do these laws seem so perfectly tailored for our existence in the first place? This line of inquiry leads us directly to the anthropic principle, a concept that is both a fascinating insight and a potential cosmic cop-out. In its simplest form, the anthropic principle suggests that the fundamental constants and laws of physics appear fine-tuned for life because if they weren't, we wouldn't be here to notice. We are not observing a universe that was designed for us. We are the products of a universe whose specific and perhaps arbitrary parameters allowed for our evolution. Our existence is therefore a selection effect, our observation bias that shapes our entire perspective on reality. The philosophical implications of this principle are staggering, forcing us to confront the role of the observer in the cosmos. The physicist Brandon Carter, who coined the term in 1974, framed it as a necessary correction to our cosmic arrogance. He argued that our location in the universe is not only privileged in space and time, but also in the very values of the physical constants that govern it. Stephen Hawking further popularized this idea, often using it to explain why we find ourselves in a universe that seems so hospitable. He pointed out that the universe must be compatible with the conscious life that observes it, otherwise the question wouldn't even be asked. This isn't an explanation for why the constants are what they are. It is a logical statement about the necessary conditions for our own existence. It shifts the question from, why is the universe so perfect for life? To, what must the universe be like for us to be here to ask that question? This reasoning is powerfully illustrated by the concept of fine-tuning. Consider the force of gravity. The gravitational constant is a precise number that determines how strongly masses attract each other. If this value were even slightly stronger, the consequences would be dire. Stars, which are a delicate balance between the inward crush of gravity and the outward push of nuclear fusion, would burn their fuel at a much faster rate. A star like our Sun might not shine for billions of years, but instead for only a few million. This would drastically shorten the window of time available for life to evolve on any orbiting planets. If gravity were significantly stronger, stars would be smaller, hotter, and burn out incredibly quickly, potentially collapsing into black holes before any complex chemistry could begin. The universe would be filled with short-lived, violent stellar objects and dark remnants, utterly devoid of the long-term stability required for planets, oceans, and living organisms to emerge. This fine-tuning extends far beyond gravity. The strength of the strong nuclear force is calibrated to a razor's edge. If it were just a few % weaker, protons and neutrons would not bind together, and the only element in the universe would be hydrogen. There would be no carbon, no oxygen, no building blocks for life. If it were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for stars to burn long-term. The cosmological constant, representing the energy of empty space, is fine-tuned to an even more incredible precision. If it were a little larger, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never have formed. If it were slightly smaller, the universe would have collapsed back on itself almost immediately. The number of potential universes that are lifeless and inhospitable seems to vastly outweigh the one we happen to inhabit. This brings us to a chilling and deeply philosophical corollary to the anthropic principle regarding the silent collapse. If our universe is just one of countless possibilities, a single winning ticket in a cosmic lottery where most universes have laws that are incompatible with life, then a collapse of physical law might not be a rare or unexpected event. In fact, it could be the norm. Perhaps the silent collapse is not a future possibility for our universe, but a past and present reality for an infinite number of others. In the vast landscape of possible universes, most might be stillborn or ephemeral, their physical laws so unstable or chaotic that they flicker into and out of existence in an instant, or they endure in a barren, inert state forever. A law of physics might stop working all the time in countless other realities. The truly eerie thought is that we would never know. These collapses happen where there is no one and nothing to witness them. Our universe feels stable and lawful not because it is special, but because we are the select observers of a stable and lawful corner of a much weirder and more dangerous multiverse. Our existence is the ultimate evidence that, so far, our local rules have held, but the anthropic principle offers no guarantee that they will hold forever. For all the terrifying theoretical possibilities we've explored, a crucial question remains. Is there any actual, empirical evidence that the laws of physics might not be as constant as we believe? Have we ever caught them in the act of changing? The scientific method is built on testing and retesting, and for centuries, the constancy of physical laws has been a foundational assumption. But what happens when our instruments become so precise that they can measure the universe's most fundamental parameters across billions of years of cosmic history? This is not just philosophy, it is the cutting edge of experimental physics, a field where extraordinary claims require not just evidence but a mountain of it. One of the most famous and controversial quests in this area revolves around a seemingly innocuous number known as the fine structure constant, denoted by the Greek letter alpha. This number is what physicists call a dimensionless constant. It has no units, and it is a pure ratio combining the speed of light, the charge of an electron, and Planck's constant. Its value, approximately 1/137, governs the strength of the electromagnetic force, dictating how atoms hold together and how light interacts with matter. Because it is a combination of other constants, if alpha were found to be changing over time or space, it would imply that at least one of those fundamental building blocks, the speed of light, the electron's charge, or Planck's constant, must also be changing. It would be the first hard evidence of a silent collapse in progress. To test this, scientists needed to become cosmic archaeologists, digging into the distant past to see if the physics of ancient light matches the physics of today. The most powerful tool for this excavation is quasar spectroscopy. Quasars are the intensely bright cores of distant galaxies, acting as cosmic lighthouses shining from billions of years ago. As their light travels across the vast expanse of the universe to reach our telescopes, it passes through clouds of interstellar gas. Atoms in these clouds absorb very specific wavelengths of this light, leaving behind a unique fingerprint, a barcode of dark lines in the quasar's spectrum. The precise position of these absorption lines is exquisitely sensitive to the value of the fine structure constant. If alpha had a different value when that light was absorbed eons ago, the entire barcode pattern will be slightly shifted, not all the lines moving together, but each one shifting by a different, calculable amount. This is precisely what a team of astronomers led by John Webb of the University of New South Wales set out to measure. Using the powerful Keck telescope in Hawaii, they analyzed the light from dozens of quasars, peering back over vast cosmological distances. Their results, first published in the late 1990s and refined over decades, sent a shockwave through the physics community. They claimed to have found evidence that the fine structure constant was indeed different in the early universe, not by much, but by a statistically significant amount. According to their data, alpha was slightly smaller billions of years ago. This was not a dramatic, universe-shattering change, but a tiny, subtle drift. Yet its implications were monumental. It suggested that the laws of physics might not be written in stone, but in something more like sand, subject to slow erosion over cosmic time. Unsurprisingly, a claim this extraordinary was met with intense skepticism and rigorous scrutiny from other physicists. The measurements are phenomenally difficult, pushing our technology to its absolute limits. Critics pointed to potential systematic errors, unknown instrumental effects, the challenges of calibrating telescopes over such long observations, or the complex physics of the interstellar clouds themselves. Could the observed shifts be explained by something other than a changing constant? The debate raged in journals and at conferences. Other teams, using different methods and different telescopes, like the Very Large Telescope in Chile, initially found no such variation, further fueling the controversy. The physics community found itself at an impasse, a classic example of how science self-corrects through a slow, painstaking process of independent verification and challenge. John Webb and his team have continued their work, refining their analysis and asserting that their evidence holds up, even as others remain unconvinced. This ongoing debate is not a sign of weakness in science. It is its greatest strength, a collective effort to ensure that we are not fooling ourselves with a result we desperately want to be true. The hunt for inconstant constants isn't confined to the depths of space. It's also happening right here on Earth with unimaginable precision. In laboratories around the world, physicists use atomic clocks, the most accurate timekeeping devices ever built, to test the constancy of nature's laws. These clocks don't tick, they measure the unwavering frequency at which electrons in atoms like cesium or strontium jump between energy levels. This frequency is a direct probe of the fine structure constant. By comparing the ticking rates of different types of atomic clocks over months and years, scientists can search for any tiny drift between them. If the fundamental constants governing each atom's energy levels were changing at different rates, the clocks would slowly fall out of sync. So far, these exquisitely sensitive Earth-based experiments have found no evidence of change, placing incredibly tight constraints on any variation. This creates a fascinating tension. Claims of a signal from the ancient, distant universe, but no signal from our local, modern neighborhood. Are the constants changing so slowly that we can't detect it in a human lifetime? Or are the quasar measurements ultimately explained by a subtle, undiscovered error? The mystery remains wide open. This entire endeavor forces us to confront a deeply unsettling hypothetical. For centuries, the scientific process has operated on the principle that any anomaly will eventually be explained within a larger, more complete framework. The history of physics is a history of crises resolved. But what if, one day, an experiment is performed that is so clean, so precise, and so independently verified that the scientific community is forced to accept a terrifying conclusion? A fundamental law of physics is genuinely, indisputably breaking down. Not because of a flaw in our theory, but because the universe itself is changing its rules. How would science, and indeed humanity, respond? The initial reaction would likely be a combination of disbelief, excitement, and profound anxiety. Every measurement in every lab would be rechecked. theorists would work frantically to develop models that could accommodate a varying constant without causing the total cosmic collapse we've imagined. It would be the ultimate scientific revolution, upending not just our understanding of the cosmos, but our place within it. We would have to accept that we live in a universe that is not only not made for us, but one that is fundamentally unstable, a ship whose very blueprint is being rewritten as we sail. The silent collapse would have moved from a terrifying thought experiment to our terrifying new reality. Yet as we sift through the ashes of a collapsed physical law, a far more unsettling question emerges, one that strikes at the very heart of our quest for knowledge. If a law of physics can fail, what does that say about the mathematics we used to describe it in the first place? We have always assumed a sacred marriage between the two, a perfect partnership where the elegant equations of mathematics somehow mirror the fundamental workings of the cosmos. But is this relationship real, or is it the greatest magic trick the human mind has ever played on itself? Are the laws of physics transcendent truths that we discover through math, or are they merely useful models, human inventions that we clumsily fit onto a universe that is ultimately unknowable? The silent collapse forces this philosophical rift wide open, challenging not just what we know, but how we can know anything at all. This profound mystery was captured perfectly by the physicist Eugene Wigner in his famous 1960 essay, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He expressed a sense of deep wonder that math, a product of human reason and abstraction, should be so spectacularly powerful in explaining and predicting the behavior of the physical world. It feels, as Wigner put it, like a miracle. We develop complex number systems and geometric theorems with no thought for their practical application, only to find generations later that they provide the perfect language for describing the orbit of planets or the spin of an electron. This uncanny partnership suggests a deep, pre-existing harmony between the logic of the human mind and the logic of the universe, as if we are somehow reading from the same cosmic script. But a silent collapse would shatter this comforting illusion. If a mathematically formulated law suddenly ceases to describe reality, it begs the question, was the math ever truly describing a real thing, or was it just a fantastically accurate but ultimately temporary approximation? This dilemma is at the core of a centuries-old philosophical battle between two schools of thought, Platonism and nominalism. A mathematical Platonist, like the ancient Greek philosopher for whom the idea is named, believes that mathematical entities, numbers, circles, equations have a real, independent existence in a perfect, abstract realm beyond space and time. When a physicist writes down an equation, a Platonist would say they are not inventing it. They are discovering a timeless, eternal truth about this metaphysical reality. The laws of physics, therefore, are glimpses into this perfect world of forms. A nominalist, on the other hand, argues that mathematics is a human invention, a sophisticated language of symbols and rules we created to organize our sensory experiences. Concepts like two or infinity are just names noumena we use for useful mental constructs. They have no independent reality outside of the human mind that conceived them. For a nominalist, the laws of physics are not discovered truths but invented tools, and like any tool, they can become dull, break, or be replaced by a better model. The history of science is filled with stunning examples that seem to support the Platonic view, none more so than the role of so-called imaginary numbers in quantum mechanics. The term itself is a historical misnomer. These numbers, based on the square root of -1, were once dismissed as a purely abstract mathematical curiosity with no possible connection to the real world. Yet when physicists were developing the framework of quantum mechanics, they found that these imaginary numbers were not just useful, they were absolutely essential. The Schrödinger equation, the very heart of quantum theory, relies on the complex plane involving imaginary numbers to accurately describe the probabilistic wave function of a particle. The mathematics demanded the existence of a tool that had been invented centuries before with no practical purpose, and that tool turned out to be the key to unlocking the behavior of the subatomic world. It was a breathtaking moment of prescience, as if the universe had been quietly waiting for us to develop the right language to speak its deepest secrets. This feels like powerful evidence for a preordained harmony, a mathematical reality that exists whether we are here to discover it or not. But the silent collapse forces us to consider the other, more terrifying possibility. If a fundamental law, expressed in a seemingly perfect mathematical form, were to stop working, what would become of the math itself? Would the beautiful equations for electromagnetism or gravity simply cease to be true, becoming nothing more than historical artifacts of a bygone cosmic era? This would be a catastrophic event for the Platonist view, suggesting the abstract realm is not so eternal or immutable after all. Alternatively, the collapse might reveal that our mathematics was never truly fundamental. Perhaps it was always just an incredibly effective approximation, a set of rules that worked wonderfully within a certain range of conditions but breaks down completely outside of them, like Newtonian mechanics failing near the speed of light. In this scenario, the math doesn't fail, our interpretation of its scope does. A physical collapse wouldn't destroy mathematics, but it would humiliate our confidence in it, revealing that our most profound equations are merely local bylaws in a universe whose true operating manual is written in a language we have not yet even conceived. This leads us to the ultimate, haunting question that hangs over all of theoretical physics. If we were to witness the silent collapse of a law, would it ultimately reveal mathematics to be a mere human construct, a temporary scaffold we built to reach an understanding that was always beyond our grasp? Or would it point toward an even deeper, more resilient mathematical truth that we have not yet uncovered, a more fundamental set of equations that can explain both the previous law's success and its subsequent failure? The collapse would not be the end of math, but a brutal and unforgiving editor, forcing us to discard our elegant but incomplete models in search of a more powerful, more universal language that can describe a reality in flux. It would be the ultimate test of whether the universe is truly, as Galileo proclaimed, a grand book written in the language of mathematics, or whether we have merely been projecting our own linguistic order onto a chaos that is ultimately indifferent to our equations and our existence. If the very laws that define our reality were to suddenly shift or fail, we are forced to confront a question that has haunted philosophers for millennia, a question that goes far beyond physics and strikes at the very core of what it means to know anything at all. What is real? For centuries, we have operated on the assumption that the universe operates according to a consistent, rational set of rules that we can, through careful observation, eventually understand. This trust in a stable, objective reality is the bedrock of the entire scientific endeavor, but a silent collapse would shatter that foundation, suggesting that the rules are not just unknown but fundamentally unstable. It would transform the cosmos from a comprehensible mechanism into a capricious and unpredictable entity, leaving us adrift in a sea of doubt where nothing could be taken for granted. This descent into radical uncertainty has a profound historical precedent in the work of the 17th century philosopher René Descartes. In his seminal Meditations, Descartes engaged in a thought experiment of extreme skepticism, attempting to doubt everything he thought he knew in order to find a single, indubitable truth upon which to rebuild knowledge. He envisioned the possibility of an evil demon, a powerful and deceitful entity capable of manipulating all his senses and thoughts, creating an entire illusory world for him to inhabit. The only thing he could not doubt was his own act of thinking, leading to his famous conclusion, cogito ergo sum, I think, therefore I am. Descartes used this demon to separate the certain reality of his own consciousness from the potentially false reality of the external world. A silent collapse of physical law would be the modern, scientific equivalent of Descartes' demon. It wouldn't be a malicious entity tricking us, but the universe itself revealing that the external reality we've meticulously mapped is not fixed. The demon is no longer a thought experiment. It is the terrifying possibility that the cosmos is inherently unreliable. This line of thinking finds a powerful and disturbing resonance in one of the most discussed philosophical ideas of the 21st century, the simulation hypothesis. Popularized by the Oxford philosopher Nick Bostrom, the argument suggests that if a civilization could ever reach a level of technological maturity capable of running vast, detailed simulations of conscious beings, then the number of simulated minds would likely vastly outnumber the biological ones. Therefore, statistically, we are more likely to be living in a simulation created by an advanced civilization than in the base, physical reality. In this context, the laws of physics are not fundamental truths of nature. They are merely the source code of the simulation, the programmed rules that govern the virtual environment. The silent collapse then takes on a new and even more unsettling character. It wouldn't be a natural disaster, but a glitch in the matrix. It could be a corruption of the code, a running error, or perhaps even an intentional update or patch applied by the simulators. The failure of gravity or the speed of light would be no different than a bug in a video game causing characters to clip through walls or physics to behave erratically. Our fear shifts from the awe of a broken universe to the existential terror of realizing we might be living in a program that is starting to fail. This forces us to a crossroads of understanding that is both terrifying and strangely liberating. On one hand, such an event would seem to be the ultimate epistemological catastrophe, undermining the entire edifice of human knowledge. Every scientific discovery, every technological achievement, every prediction about the future would be rendered null and void, built as they were upon a set of rules that are now revealed to be temporary or local. Our confidence in reason itself would be broken. How could we ever trust any observation or experiment again if the underlying constants of reality are subject to change? We would be plunged into a new dark age, not of ignorance but of radical uncertainty, where the tools of science can no longer provide assured answers. Yet, on the other hand, a collapse could also be seen as the ultimate scientific revelation. It would force upon us a paradigm shift so profound that it would open doors to new ways of understanding existence that we cannot currently even conceive. Just as the failure of Newtonian mechanics led to the revolutions of relativity and quantum physics, the failure of all known laws would be the catalyst for a new and deeper physics, one that could account for a reality in flux. It might reveal that our universe is just one domain within a much larger and more complex multiverse, each with its own unique set of physical bylaws. The collapse would not be an end, but a brutal and necessary beginning, shattering our limited models to make way for a truer, if far stranger, comprehension of the cosmos. The choice is between seeing ourselves as victims of a chaotic universe or as students on the verge of the greatest lesson reality has ever taught. Now, let's pull our gaze back from the quantum realm and expand it to the grandest canvas of all, the cosmos itself. The silent collapse of a fundamental law would not be contained to our planet or even our solar system. Its repercussions would ripple outward at the speed of causality itself, unraveling the largest structures in the universe in a breathtakingly short amount of time. To understand this, we must first appreciate the majestic architecture of the cosmos as we know it. Thanks to instruments like the Hubble and James Webb Space Telescopes, we have stunning images of spiral galaxies like Andromeda, their elegant arms gracefully swirling around a brilliant core, each one a gravitationally bound island of hundreds of billions of stars. We see the serene glow of nebulas, the stellar nurseries where new suns are born, and the violent, beautiful aftermath of supernova, which seed the galaxy with the elements for planets and life. This is a universe of breathtaking order and clockwork precision on a scale that defies human comprehension. The first and most dramatic casualty of a universal law failure would be the galaxy itself. These immense structures are held together by one thing and one thing only: gravity. The immense collective mass of all those stars, gas clouds, and the mysterious dark matter halo creates a gravitational well so deep that every component is locked in a perpetual orbital dance. If the law of gravity were to weaken or alter its behavior, that entire delicate balance would instantly vanish. It would be as if the strings holding a marionette were suddenly cut. The graceful spiral arms would not just slowly unwind, they would violently fly apart. Stars would be flung from their orbits like sparks from a pinwheel, hurled out into the cold, dark emptiness of intergalactic space. The galaxy would cease to be a coherent structure, dissolving into a diffuse and expanding cloud of isolated stars, each one set adrift on a lonely, unpredictable trajectory. The iconic image of the spiral galaxy would become a cosmic memory, replaced by a formless, chaotic smear of light. Within this dissolving galactic framework, the individual stars themselves would face their own apocalyptic fates. A star is a perfect example of a stable system maintained by the precise balance of opposing forces. For millions or billions of years, the inward crush of its own immense gravity is perfectly counteracted by the outward pressure from nuclear fusion in its core. This equilibrium is what makes a star shine steadily. But if a fundamental constant governing nuclear forces or gravity were to change, that equilibrium would be catastrophically broken. The consequences would depend on which way the balance tipped. If the inward force of gravity suddenly gained the upper hand, stars would experience a violent, premature implosion. A star like our Sun could collapse in on itself in a matter of hours, potentially triggering a shock wave that would blow off its outer layers in a makeshift, chaotic pseudo-supernova. Conversely, if the nuclear forces faltered, the fusion furnace at the star's heart would simply snuff out. The outward pressure would vanish, and the star would begin to cool and dim, not with a bang, but with a whimper, collapsing into a cold, dark cinder over a much shorter time frame than its natural life cycle would allow. The familiar patterns of the night sky, constellations etched into human culture for millennia, would flicker, change, and ultimately vanish as these stellar engines stutter and die. And then there are the most extreme objects in the universe, black holes. We often think of them as unstoppable cosmic vacuums, the ultimate endpoints of gravity. But even they are subject to the laws of physics, and their behavior would be thrown into utter chaos by a silent collapse. According to Stephen Hawking's groundbreaking work, black holes are not entirely black. They slowly evaporate over astronomical timescales by emitting Hawking radiation, a process that relies on the subtle interplay of quantum mechanics and gravity near the event horizon. If the rules governing this process were to change, the evaporation could accelerate exponentially. A supermassive black hole, which would normally take longer than the current age of the universe to evaporate, could vanish in a spectacular flash of gamma rays in a matter of centuries, days, or even seconds. Alternatively, if gravity were to behave unpredictably, the event horizons of black holes could become unstable. Two black holes orbiting each other, destined to merge in a distant future, might instead be torn apart by a sudden shift in the gravitational constant. Or their merger could become a chaotic, unpredictable event, spraying gravitational waves across the cosmos in a discordant rhythm rather than the precise chirp we've learned to detect. The anchors of the galactic center would be unmoored, leading to a final, frenzied act of destruction. The sheer scale of this loss is what makes it so difficult to grasp. Astrophysicist Neil deGrasse Tyson often speaks to this fragility, reminding us that cosmic order is not a given. He has eloquently described our universe as a cosmic fugue, a vast and complex piece of music with themes of gravity, nuclear forces, and electromagnetism all playing in a harmonious billion-year-long symphony. A single law failing would be like a musician suddenly playing a devastatingly wrong note, a dissonance so profound that it would cause the entire orchestra to fall into screeching, catastrophic noise. The evolution of the universe, a story written over 13.8 billion years, from the first stars igniting to the formation of planets and the delicate emergence of life, could be erased not in an epoch, not in a millennium, but in a handful of moments. The silent collapse is the ultimate cosmic reset button, one that could undo the patient work of cosmic evolution in the blink of an eye, returning the universe to a state of primordial simplicity and leaving behind a cold, dark, and lifeless void where galaxies, stars, and the potential for wonder once existed. But while the cosmos itself would be torn apart by the failure of a physical law, the most intimate and immediate catastrophe would unfold within every living thing, a silent, internal apocalypse that would erase the very concept of biology. Life is not a separate phenomenon operating outside the rules of physics. It is the most intricate and delicate expression of those rules, a complex dance of molecules and energy that is exquisitely fine-tuned to the universe's specific constants. From the largest whale in the ocean to the smallest microbe in the soil, every organism is a walking testament to the precise, unwavering laws that govern reality. To alter those laws is not to challenge life, it is to unwrite its very definition. Consider the miraculous processes happening within your own body at this very moment. The enzymes that catalyze the chemical reactions keeping you alive, for instance, rely on a bizarre quantum mechanical trick called quantum tunneling. These protein machines facilitate reactions by helping electrons and protons jump from one molecule to another. Classical physics would suggest these particles don't have enough energy to make the jump, but thanks to the probabilistic nature of the quantum world, there's a tiny, calculable chance they can simply tunnel through the energy barrier. This quantum weirdness isn't a minor footnote. It is essential for processes like DNA repair and cellular respiration. If the rules of quantum mechanics were to fail, if particles suddenly became predictable and lost this probabilistic fuzziness, these enzymatic processes would grind to a halt. The machinery of your cells would seize up, not from a lack of fuel, but from a fundamental change in the rules of motion at the subatomic level. This reliance on physics extends to the very system you're using to understand these words, your nervous system. Every thought, sensation, and movement is governed by the flawless operation of electromagnetism. Your neurons communicate through action potentials, which are essentially waves of electrically charged ions, sodium and potassium, flowing in and out of the cell membrane. This elegant electrical signaling is a masterpiece of electromagnetic engineering. If the electromagnetic force were to weaken or become unpredictable, this entire system would fail. The precise voltage gradients that allow a signal to travel from your brain to your toe would dissolve. You might experience a fleeting moment of confusion, a last chaotic burst of neural noise before consciousness itself simply flickered out. Your mind, your memories, your very sense of self are all emergent properties of a physical system that is utterly dependent on a specific, unchanging strength of a fundamental force. And at the very core of it all is DNA, the molecule of life, whose legendary double helix structure is a monument to stability. That stability is not a given, it is a hard-won victory against constant assault. The bonds that hold the sugar-phosphate backbone together are electromagnetic, while the strong nuclear force within every atom of that structure ensures the atomic nuclei themselves don't fly apart. DNA is constantly being damaged by radiation and random thermal fluctuations, and a vast, sophisticated cellular machinery is always at work repairing it, a process that itself depends on the precise laws of chemistry and physics. If the strong nuclear force were to weaken even slightly, the atoms in your DNA could become unstable, undergoing radioactive decay and shattering the molecule from within. Alternatively, if electromagnetism faltered, the hydrogen bonds that hold the two strands together would vanish, and the elegant helix would simply unzip and drift apart into a useless molecular soup. The genetic blueprint for building and maintaining a living organism would be irreparably erased in an instant. We often look to Earth's extremophile life forms thriving in boiling hydrothermal vents, in acidic lakes, or in the crushing pressures of the deep sea as examples of life's incredible resilience. And they are, but their resilience exists within a very specific and unchanging framework of physics. An extremophile is adapted to an extreme environment, not to extreme laws of nature. A microbe that can survive intense radiation does so because its DNA repair mechanisms are exceptionally efficient, leveraging the same reliable physics to fix damage faster than it occurs. No organism on Earth or anywhere we can conceive of could adapt to a change in the fundamental constants. How could evolution possibly select for a trait that allows a creature to survive the reversal of gravity or the failure of electromagnetism? These are not environmental pressures, they are changes to the very stage upon which the play of evolution is performed. If the stage itself dissolves, the play must end. This profound fine-tuning is the central puzzle of astrobiology. As we search for life beyond Earth, we don't just look for water or a temperate climate, we look for environments where the physics is familiar. We assume that alien life, no matter how bizarre its biochemistry, would still be based on chemistry, which is itself based on the electromagnetic force. It would need stable atoms, courtesy of the strong nuclear force, and it would likely use liquid water as a solvent, a property dictated by the specific electromagnetic properties of the hydrogen and oxygen atoms. The search for extraterrestrial life is at its heart a search for places where the local conditions allow the universal laws of physics to produce the same complex, self-organizing structures we see on Earth. A silent collapse would therefore be the ultimate great filter, not just for humanity, but for any and all life everywhere in the cosmos, a universal extinction event that would leave the universe permanently barren, its potential for consciousness and wonder extinguished forever. This realization brings a chilling but also strangely beautiful perspective to our own existence. The fact that you are here, right now, reading these words, is not just a happy accident of biology on a single planet. It is the culmination of a cosmic conspiracy, a universe that has maintained its rules with unwavering consistency for over 13 billion years, allowing for the formation of stars, the forging of elements, the assembly of planets, and the impossibly delicate dance of molecules that led to you. Your consciousness is the universe becoming aware of itself, and that awareness is perched on a razor's edge, dependent on a set of physical constants that have not, so far, betrayed that trust. To contemplate a silent collapse is to understand the profound precariousness of it all, to appreciate the breathtaking fragility of every breath, every heartbeat, and every thought, all of which are gifts from a universe that has, for now, chosen to play by a set of rules that make our existence possible. The glow of your smartphone screen, the hum of your refrigerator, the precise navigation guiding your drive, these are not just conveniences of the modern age. They are the direct and miraculous offspring of our understanding of physics. Every piece of technology we have ever built, from the simplest lever to the most complex particle accelerator, is a physical argument. It is a device that says, "I trust that the universe will behave this way every single time." Now imagine that trust being broken. The silent collapse of a fundamental law would not be some distant astronomical event. Its first and most devastating blows would land right here, in the palms of our hands and the infrastructure of our daily lives, triggering a technological apocalypse that would unravel civilization in minutes. The immediate impact would be a symphony of failure, a cascading series of silences and sparks as the principles underpinning our devices ceased to function. It would begin with the electronics that form the nervous system of our world. The microprocessors in your phone and computer rely on the predictable flow of electrons through silicon, a process governed by the unwavering rules of quantum mechanics and electromagnetism. If those rules changed, the result wouldn't be a simple malfunction. The delicate, nanoscale pathways within a computer chip would experience catastrophic short circuits as electrons began to flow in unpredictable ways, following new, unknown laws. Screens would not just go dark, they might flicker with bizarre, chaotic patterns before melting into uselessness. The global network of data centers, the cloud, that holds our collective knowledge, finances, and communications, would not just shut down. It would physically destroy itself from the inside out in a wave of fried circuitry and melting solder. The internet would vanish not with a whimper, but with the smell of ozone and burning plastic. This wave of destruction would race from the digital realm to the mechanical, striking the very engines of our mobility. The internal combustion engine in a car is a carefully controlled series of explosions, a process that depends on the precise timing of spark plugs igniting a fuel-air mixture at the exact moment of maximum compression. The thermodynamics of this process, the way heat expands gases to drive pistons, is a direct application of physical laws we take for granted. If those laws became unreliable, the perfectly timed dance inside an engine would become a chaotic, stalling mess. Pistons would seize, fuel would fail to ignite or explode at the wrong time, and every vehicle on the planet would shudder to a permanent halt within seconds. The skies would fall silent as jet engines, even more complex and dependent on precise aerodynamics and material science, would simply quit, turning airliners into gliders for a few terrifying moments before gravity took over. The immense generators in power plants, whether powered by coal, gas, nuclear fission, or even the wind turning massive turbine blades, would all fail for the same reason. They are all giant machines that convert one form of energy to another using principles that would have just been revoked. Perhaps the most dramatic and immediate symbol of this collapse would unfold overhead in the silent void of space. Our planet is encircled by a fragile shell of satellites, thousands of them, each one a testament to our mastery of physics. They are there for communication, weather forecasting, espionage, and science, but most critically for our daily navigation, there is the global positioning system. We use it so casually that we forget it is one of humanity's most profound tributes to Einstein's theory of relativity. Each GPS satellite contains an incredibly precise atomic clock. Because these satellites are moving at high orbital speeds and are in a slightly weaker gravitational field than we are on Earth's surface, time itself passes for them at a different rate, a few microseconds per day faster, to be exact. This is not a theoretical curiosity. It is a real-world effect of time dilation predicted by relativity. If the ground stations did not constantly correct for this difference, the entire GPS system would become inaccurate by several kilometers within a matter of hours. Our entire understanding of location is built upon the fact that the laws of relativity are absolutely, unerringly true. If those laws were to falter, the satellites wouldn't just send wrong signals, their very orbits would become unstable. The delicate balance between their forward momentum and Earth's gravitational pull would be broken. We would look up and see them not as fixed stars, but as wandering, dying lights streaking across the atmosphere as they began to tumble from the sky, their silent fall marking the end of our global connectedness. Futurists and engineers have long warned of society's vulnerability to technological shock, though they usually envision cyber attacks or solar flares, not a change in the laws of nature. Thinkers like Elon Musk have spoken about the fragility of our technological stack, how it is built layer upon layer with the assumption that the foundation is solid. A silent collapse would be the ultimate penetration of that foundation. It would not be an attack on the technology itself, but on the logical premises that make the technology possible. We would not be able to rebuild or reboot. How do you redesign a circuit board when the behavior of electricity is no longer predictable? How do you forge a new engine when the properties of metals and the laws of thermodynamics have become variable? Innovation wouldn't just stall. It would reverse, hurtling us back into a pre-industrial darkness from which there might be no return, because the very rules for creating light would have been lost. Take a moment to mentally walk through your day and catalog the technologies you interact with before you even leave the house. Your alarm clock, the LED light you switch on, the water pressure from your shower pump, the magnetic field heating your induction stove, the radio waves bringing you the news, the car you drive or the train you take, every single one is a prisoner of physics. This exercise isn't meant to incite fear, but to inspire a profound appreciation. Our entanglement with physical law is not a weakness, it is our greatest strength. It is the framework that has allowed us to reach beyond our biological limits and shape our world, but it is also a reminder of our profound dependence. We have woven a civilization from the threads of constants we did not create and cannot control, building a magnificent tapestry on a foundation we must simply hope remains firm. The silent collapse of technology would be the ultimate demonstration that our mastery is an illusion, that we are not the masters of the universe, but its guests, living in a house whose rules we did not write and whose stability we must never take for granted. The collapse of our technological systems would be merely the opening act of a far greater tragedy, a prelude to the total disintegration of the economic and social structures that hold our global civilization together. We have built a world of breathtaking interdependence, a house of cards where each level is precariously balanced upon the one below it, and the entire edifice rests on the unwavering foundation of predictable physics. When that foundation is pulled away, the secondary effects would cascade through every aspect of human life with a speed and ferocity that would make recovery impossible. The first and most critical system to fail would be energy production. Every power plant on Earth, from a massive nuclear facility to a single solar panel on a rooftop, operates on principles of physics that would have just been rendered null and void. The controlled fission in a reactor core, the electromagnetic induction in a turbine generator, the photovoltaic effect in a solar cell, all of it would cease to function. The lights wouldn't just go out, the very means of creating light would be gone. Without energy, the pumps that move water to our cities would stop. Without water, agriculture and basic sanitation collapse within days. The intricate global supply chain, a just-in-time miracle of logistics that delivers food from across the world to your local supermarket, would freeze solid. Trucks with dead engines would litter the highways, container ships would drift helplessly at sea. The digital ledger of the entire global economy would vanish into the ether, rendering bank accounts, stock holdings, and currencies meaningless abstractions. Wealth would instantly revert to what you could physically hold, protect, and barter. This leads to the most immediate and visceral threat, the collapse of our food systems. Modern agriculture is not a natural process. It is a high-yield chemical engineering feat entirely dependent on the laws of physics and chemistry holding true. The artificial fertilizers that feed nearly half the world's population are produced in massive industrial plants using the Haber-Bosch process, a procedure that relies on precise high temperatures and pressures to fix nitrogen from the air. If the underlying principles of thermodynamics and chemical bonding fail, this process becomes impossible. But the problem runs even deeper. The very act of photosynthesis, the foundation of the entire planetary food web, is a quantum mechanical process where photons of light are captured by chloroplasts in plant cells to create energy. If the rules governing electromagnetism or quantum biology are altered, this miraculous process could stop. Crops in the field wouldn't just wither from a lack of fertilizer. They could literally cease to function at a cellular level, their biological programming corrupted by a change in the universe's source code. The silent collapse would trigger a silent famine on a scale beyond human comprehension, leaving billions to face starvation without a single harvest to hope for. We can look to history for examples of civilizational collapse, but they offer only a faint and comforting echo of the terror a universal law failure would bring. Sociologists and historians like Jared Diamond have meticulously documented the fall of complex societies, from the Maya to the inhabitants of Easter Island to the Bronze Age civilizations of the Mediterranean. These collapses were typically caused by a cascade of interconnected problems: environmental degradation, climate change, famine, war, and the failure of political institutions to adapt. They were horrific, but they were also local and slow-moving, unfolding over generations. Crucially, they occurred within a stable physical reality. When the Roman Empire fell, gravity still worked. When the Akkadian Empire collapsed due to drought, chemistry still worked. People could flee to new lands, fall back on older subsistence technologies, or slowly rebuild. The silent collapse offers no such refuge. There is no new land to flee to when the entire planet is undergoing the same catastrophic change simultaneously. There is no older technology to revert to when the axe you might use to chop wood can no longer rely on the rigidity of its steel head or the strength of your arm, both properties dictated by electromagnetic forces. This would not be a return to the Stone Age. It would be a descent into a reality with no age at all, a state of nature where nature itself has become alien and hostile. This brings us to the most harrowing question of all. In the face of such an absolute and incomprehensible catastrophe, what would become of us as a social species? Our societies are built on a foundation of shared reality and predictable cause and effect. We have laws because we can predict that a falling rock will injure someone. We have commerce because we can trust that an exchanged good will retain its properties. We have science because we believe the universe is consistent. If that consistency vanishes, so too does the basis for cooperation, trust, and social order. The initial response would likely be mass confusion, followed rapidly by primal fear. Without any rational framework to explain what was happening, superstition, paranoia, and scapegoating would flourish. The social contract, that fragile agreement to cooperate for mutual benefit, would shatter, replaced by a desperate struggle for the most basic resources: clean water, safe food, and shelter that wouldn't dissolve around you. The institutions designed to protect us, governments, police, armies, would be among the first to fail as their command and control structures dissolved and their personnel abandoned their posts to protect their own families. In the absence of authority, human resilience would be tested against the rising tide of human desperation. The knowledge required to rebuild, the accumulated wisdom of centuries of science and engineering, would be useless because it would be a textbook for a game whose rules had changed. The greatest threat to humanity's survival might not be the collapse of physics itself, but the collapse of the human spirit in the face of an utterly meaningless and chaotic universe, where ignorance and fear become the only constants left. Yet as our global systems shudder and fail, the most profound and personal devastation would not be happening out in the world, but within the confines of our own minds. We are meaning-making creatures, and our entire existence is built upon a foundational, unshakable trust that reality is stable and predictable. The sun will rise, objects will fall when dropped, and our memories provide a reliable record of our past. This trust is so deeply ingrained that we are almost never consciously aware of it. It is the silent operating system of human consciousness. A silent collapse would be more than a physical catastrophe. It would be a direct assault on that operating system, triggering a psychological crisis of unprecedented scale. The initial human response would likely be a wave of profound, paralyzing confusion. Imagine waking up to a world where your own senses betray you. You reach for your glasses on the nightstand, but your hand passes through them. You look out the window and see birds hanging motionless in the sky, defying gravity. The very data streams your brain uses to construct a coherent model of the world are now feeding it nonsense. This isn't like witnessing a magic trick where you know there's a logical explanation you're not seeing. This would be the terrifying realization that logic itself has broken down. The cognitive dissonance, the mental stress and discomfort experienced when holding two contradictory beliefs would be immediate and overwhelming. The core belief, the world is predictable, would violently clash with the new evidence, the world is not predictable, creating a psychological wound that the mind would desperately try to heal. This desperate search for coherence would inevitably lead us down the path of denial, a classic psychological defense mechanism we use to protect ourselves from unbearable truths. In the face of an inexplicable event, our first instinct is not to accept the new reality, but to find a reason why it can't be true. We would concoct 1,000 rationalizations before accepting that the laws of physics have changed. People would insist it was a mass hallucination, a sophisticated global hack, or an elaborate social experiment. They would blame everything from contaminated water supplies to secret military weapons. This denial would be a temporary life raft in a sea of chaos, a way to preserve a sliver of the old, understandable world. But as the anomalies continued, as food failed to nourish, as structures continued to dissolve, as the very air became difficult to breathe, that life raft would spring leaks. The defense would crumble, making way for the raw, primal emotion lurking beneath the surface, existential terror. This is a fear far deeper than the fear of death. It is the fear that the universe itself is meaningless, chaotic, and hostile. It is the realization that the story we tell ourselves about reality, a story of cause and effect, of past and future, of a universe that can be understood, was just a comforting fairy tale. The foundation of knowledge itself would be swept away, leaving the human psyche adrift in an ocean of absurdity. The study of how we perceive and construct reality offers a chilling lens through which to view this crisis. Renowned cognitive psychologist Elizabeth Loftus has spent decades demonstrating the incredible malleability of human memory. Through her seminal work, she has shown that memories are not perfect recordings of past events, but reconstructions that are easily influenced by suggestion, misinformation, and even our own beliefs. We don't retrieve memories, we recreate them each time we recall them, and in the process we can alter them without ever realizing it. Loftus's research proves that our most cherished personal histories are far less reliable than we imagine. Now extrapolate this fragility to a world where external reality itself is no longer stable. If we cannot even trust our internal record of events, and we can no longer trust the external world to behave consistently, the very concept of truth evaporates. Your memory of eating breakfast this morning could be an illusion, and your attempt to verify it by looking for crumbs could be thwarted by a law of physics that causes matter to appear and disappear randomly. This double assault on internal and external validation is a recipe for mass psychosis, a state where a society loses its shared grip on reality. Without a common reality to anchor them, groups would fracture into isolated pockets, each clinging to their own explanation, their own new mythology for a broken world. Conspiracy theories would flourish not as fringe ideas, but as necessary survival mechanisms, the only way to impose a narrative, any narrative, onto the chaos. Picture the scenarios that would unfold on a societal level. A parent comforting a child, promising them that everything will be okay, while secretly watching the walls of their home begin to waver and lose solidity. A scientist in a lab desperately trying to run a simple experiment, only to get a different result every single time, descending into a vortex of despair as the methodology of a lifetime becomes useless. Neighbors turning on each other not for resources, but out of a deep-seated fear that the person next door might be the cause of, or somehow immune to, the unfolding horror. Social order, which is ultimately a shared agreement on how reality works, would disintegrate into paranoid anarchy. The institutions we look to for stability, governments, universities, religious organizations, would be powerless, their authority derived from a world that no longer exists. This forces a deeply personal reflection on how much we take for granted. We move through our days with an implicit faith in the continuity of experience. We trust that the floor will support us, that our memories are our own, and that the person we spoke to yesterday will be the same person today. This trust is the invisible glue of our daily lives and our mental well-being. So what mental frameworks could possibly help in such an unimaginable crisis? Perhaps the only defense would be a radical acceptance of the present moment, a mindfulness so intense that it relinquishes all need for prediction and control. Eastern philosophies like Buddhism have long taught about the impermanent and illusory nature of the perceived world, suggesting that suffering comes from our attachment to a stable, permanent self and reality. In a sense, a silent collapse would be the brutal, forced enlightenment of all humanity. The only way to retain one's sanity might be to let go of the need to understand and simply experience, moment by fleeting moment, without expectation. It would require building a new sense of self that is not defined by a consistent past or a predictable future, but that exists only in the ever-changing, unreliable now. This is not a comforting thought. It is a monumental psychological challenge, yet it highlights the incredible resilience of the human spirit, its ability to seek meaning even in the face of meaninglessness, and to find a way to endure even when the universe itself seems to have withdrawn its fundamental consent. When the very rules of reality itself begin to disintegrate, humanity's search for meaning would inevitably turn from the laboratory to the sanctuary, from the language of equations to the language of faith. Across the globe and throughout history, when confronted with the inexplicable, we have sought answers not in the how but in the why. A silent collapse, an event of such profound and absolute chaos, would be the ultimate test for every theological framework ever conceived. Would it be interpreted as the ultimate act of divine intervention, a final judgment, or perhaps a cosmic test of faith on a scale beyond human comprehension? The answers would vary dramatically depending on the spiritual lens through which this catastrophe was viewed. Within the Abrahamic traditions, Judaism, Christianity, and Islam, the concept of a miracle is central. A miracle is traditionally understood not as a breaking of God's laws, but as a divine suspension of them for a specific purpose, a sign of divine power and will. The parting of the Red Sea, the resurrection of Christ, the miraculous provisions in the Quran, these are all seen as God intervening directly in the natural order. A silent collapse, however, would be a suspension of law without any apparent purpose, direction, or message. It would be chaos, not a sign. This would present a profound theological crisis. Could such an event be seen as a form of divine punishment, a modern-day flood for a globalized, technologically prideful humanity? Some might certainly interpret it that way, seeing in the unraveling of atoms a reflection of a moral unraveling. Others might view it as a test of faith far more severe than that of Job, a challenge to maintain belief in a benevolent, omnipotent God, even as the fabric of his creation visibly and violently frayed. The very idea of a covenant, a promise of order and natural law from the divine, would be called into question, forcing a radical reinterpretation of humanity's relationship with the Creator. Eastern philosophies like Hinduism and Buddhism offer a different framework, one not of a singular divine lawgiver, but of an impersonal, cyclical cosmic order known as Dharma, or the working of karma. In these views, the universe operates according to principles of cause and effect that span across lifetimes. A physical law's failure wouldn't be seen as the action of a capricious deity, but as a symptom of a deeper cosmic imbalance. It might be interpreted as the universe entering a particularly dark and chaotic phase within its vast cycle of creation, preservation, and dissolution, a period akin to the Kali Yuga in Hindu cosmology, where disorder reigns before an eventual renewal. The concept of karma, where individual and collective actions have consequences, could be expanded to a cosmic scale. The collapse could be seen as the ultimate karmic repercussion for a civilization that lost its way, that exploited nature without understanding its sacred interconnectedness. The appropriate response, then, wouldn't be prayer for deliverance but a focused effort on individual and collective righteousness to help restore balance, even in the face of overwhelming chaos. This fascinating dialogue between the mechanistic and the metaphysical is embodied by figures like Francis Collins, the renowned geneticist and devout Christian who led the Human Genome Project. Collins speaks often of the concept of biologos, a harmony between science and faith where natural laws are the elegant language through which a creator God sustains the universe. For someone like Collins, the discovery of these laws is an act of worship, a reading of the book of God's works. But how would such a perspective reconcile with the erasure of that very language? A silent collapse would represent the ultimate challenge to this harmonious view. It would force a painful choice. Either God is directly, and seemingly chaotically, intervening in a way that contradicts his own nature as a God of order, or the laws were never truly fundamental in the first place, but merely a temporary grace, a stable platform granted for a time to allow for life and discovery. This wouldn't necessarily destroy faith, but it would demand a faith that is far more mysterious and less comfortably rational, a belief in a deity whose methods and purposes are entirely inscrutable. This leads each of us to a moment of profound personal reflection. If you were to witness the stars winking out and the ground losing its solidity, where would you turn for explanation? For comfort? Would the total failure of predictability drive you to conclude that the universe is ultimately godless, a random assemblage of rules that can simply stop working? Or would it have the opposite effect, pushing you toward the belief that such an incomprehensible event must be the work of a power so far beyond our understanding that it can only be called divine. The collapse would force a raw, primal assessment of what we truly believe about purpose, agency, and the existence of a reality beyond the physical. For some, the silent collapse would be the final, definitive argument for atheism, proof that the universe is governed by blind chance and fragile order. For others, it would be the ultimate proof of the divine, an event so colossal and beyond nature that it points irrevocably to the supernatural. In the echoing silence left by broken physics, the only sound would be the whispered questions of billions of souls searching for a reason in the ruins. In the immediate, stunned aftermath of the first undeniable signs of a silent collapse, the global scientific community would find itself in a position no amount of education or experience could ever prepare them for. This wouldn't be a puzzle to be solved. It would be the very framework of their puzzle-solving toolkit being systematically dismantled. The initial reaction would likely be a profound and collective cognitive dissonance, a refusal to accept the data staring back from their instruments. Scientists are trained to be skeptics, to first assume error in their equipment or their methods before ever questioning the foundational laws of nature. There would be a frantic, global effort to recalibrate sensors, to check for solar flares or other cosmic interference, to rule out any conceivable mundane explanation. But as the anomalies continued to mount, as gravity meters gave nonsensical readings in labs from Tokyo to Geneva, as particle accelerators began producing results that violated centuries of established theory, that denial would curdle into a chilling, unprecedented realization. The problem wasn't with their instruments, the problem was with reality itself. This realization would trigger the largest, most urgent mobilization of intellectual resources in human history. International rivalries and competitive silos would shatter overnight, replaced by a desperate global collaboration. Physicists from every nation and every subdiscipline would be united by a single, terrifying question: what is happening? Data streams from every major observatory, collider, and satellite would be fused into a single, open-source global network, a nervous system for a planet in shock. The world's most powerful supercomputers, once used to model climate or simulate nuclear explosions, would be retasked with a singular purpose, running endless simulations to find any new set of equations, any theoretical framework, no matter how bizarre, that could possibly account for the cascading failures. This wouldn't be a normal scientific revolution like the shift from Newtonian mechanics to relativity. Those were paradigm shifts within a stable system of rules. This would be a revolution against the system itself, a fight for a new rulebook while the old one was actively burning in their hands. We can look to history for echoes of this kind of frantic, collaborative energy, but only as a faint whisper compared to the roar this event would generate. The Manhattan Project saw brilliant minds gathered under immense pressure, but they were working with known, reliable physics to achieve a defined engineering goal. The race to decode the genome was a competitive but ultimately orderly process. The silent collapse would be orders of magnitude more profound. There would be no textbook to consult, no underlying principle to fall back on. The very process of the scientific method, forming a hypothesis, testing it with an experiment, and expecting a predictable result would be compromised. How do you test a new theory about gravity when the force of gravity might be different tomorrow, or might not even exist in the same way in the lab next door? The chaos wouldn't just be in the world, it would be inherent to the process of investigation itself. In this maelstrom of uncertainty, the role of our largest experimental facilities would transform dramatically. Take the Large Hadron Collider at CERN. Normally, It's a precision instrument used to probe the edges of known physics, smashing particles together to find new ones or verify predictions. In a crisis, it would become a canary in a coal mine, a massive and exquisitely sensitive barometer for the stability of physical law. If the strength of the strong nuclear force began to fluctuate, the debris from particle collisions would become a chaotic, unpredictable mess. The delicate detectors, designed to measure known quantities with incredible precision, would be flooded with impossible data. The collider wouldn't be a tool for discovery anymore. It would be a diagnostic instrument, its operators desperately trying to measure the rate and nature of the decay, to see if any patterns or constants remained amidst the growing chaos. It would be a frantic attempt to take the universe's vital signs as it went into systemic failure. Living physicists who have spent their careers contemplating the edges of knowledge would suddenly find their speculative theories terrifyingly relevant. Michio Kaku, a renowned futurist and co-founder of string field theory, has long spoken about the importance of what he calls Type 4 civilizations, those that can manipulate the very laws of physics themselves. He often discusses the need for a cosmic insurance policy, the importance of becoming a multi-planetary species to survive existential threats. Faced with a silent collapse, his warnings would feel less like speculation and more like a devastatingly prescient obituary for a civilization that failed to heed them. The scientific response would have to grapple with Kaku's core question: how does a species prepare for the truly unknown? The answer, in the midst of the collapse, would be that you can't. You can only respond with a blend of rigorous discipline and radical open-mindedness, desperately trying to build a lifeboat from the very planks of the ship that are dissolving around you. This unprecedented crisis would immediately force a series of brutal ethical dilemmas upon the scientific community and world leaders. With society crumbling outside their lab walls, would it be ethical to continue pouring vast resources, precious remaining energy, computational power, and the focus of brilliant minds into purely theoretical research? Or would every effort need to be directed toward immediate, practical survival? Even more disturbing, the desire to understand might lead to dangerously intrusive experiments. If a theory emerged that suggested localized phenomena could be stabilized or even reversed, would it be ethical to test it, even if there was a risk of accelerating the collapse in that region or beyond? The history of science is littered with experiments undertaken without a full understanding of the consequences, from early nuclear tests to gene editing. But those risks were taken within a stable physical framework. Now the stakes would be incalculably higher. A failed experiment wouldn't just contaminate a site or create a dangerous technology. It could potentially unravel the last stable pocket of reality humanity had left. The scientists, once the quiet seekers of truth, would suddenly find themselves holding the fate of existence in their hands, forced to make decisions with no data, no precedent, and no certainty of anything but the profound and terrifying weight of their responsibility. Faced with the unimaginable specter of a silent collapse, our minds instinctively recoil and search for a solution, for a lever we might pull to stop the unraveling before it begins. This desperate search for agency leads us into the most speculative and awe-inspiring realms of theoretical physics and futurism, where the line between science and science fiction becomes beautifully, terrifyingly blurred. The first and most daunting question is one of early warning. Could an advanced civilization, one that has mastered the cosmos, ever detect the precursors to a fundamental law breaking down? The answer might hinge on the nature of the collapse itself. If it's a slow, cosmic drift in a constant like the fine structure constant, then perhaps. A sufficiently advanced society might deploy a galaxy-wide network of monitoring stations, each equipped with unimaginably precise instruments, quantum interferometers or space-time strain gauges constantly measuring the very fabric of reality for the faintest tremor, the subtlest shift in the universe's foundational parameters. They wouldn't be looking for a dramatic event, but for a statistical ghost, a persistent anomaly in data collected over millennia that signals a fundamental constant is no longer quite so constant. Detecting such a drift would be like hearing the first, almost imperceptible creak in the support beam of a vast cathedral, a warning that arrives long before the ceiling begins to fall. But what could they possibly do with that warning? This is where our speculation vaults into the truly extraordinary. Could a civilization not just detect, but actually engineer physical constants? The idea of tweaking the universe's dials seems like the ultimate hubris, yet some theories in physics, particularly those involving the Higgs field, suggest it might not be entirely impossible. The Higgs field is what gives fundamental particles their mass. Its value is essentially a constant that permeates all of space. In theory, a catastrophic change in this field, a phase transition to a different energy state, could rewrite the masses of particles and unravel reality. A hyper-advanced civilization might dream of developing a technology to stabilize this field, a Higgs stabilizer or a quantum anchor, a device of incomprehensible power designed to pin the field in its current state, preventing a transition. This wouldn't be a physical structure, but an energetic one, perhaps generating a localized field that reinforces the existing laws of physics, creating a bubble of stability in a sea of growing chaos. Think of it as the ultimate surge protector for reality, a device that ensures the voltage of the vacuum doesn't spike or drop and fry the circuitry of existence. The visionary futurist Isaac Arthur often explores these grand concepts of civilizational resilience on cosmic timescales. He discusses the idea of a Type 4 civilization, one that has transcended its planetary, stellar, and even galactic origins to harness the energy of the entire universe. For such an entity, a silent collapse would be the ultimate existential threat, and their mitigation strategies would be accordingly immense. Arthur talks about concepts like Jupiter brains, planet-sized computers that could run ultra-precise simulations to model the collapse and test potential countermeasures. He speculates about creating backups of physical law itself, not just data, but perhaps encoding the information of our universe's specific constants into stable, higher-dimensional structures, or even seeding baby universes with the same physics in a vast multiverse, ensuring that even if our local reality fails, the recipe for a life-friendly cosmos persists elsewhere. This isn't about saving one planet or one species. It's about cosmic-scale conservation, treating the laws of physics themselves as the most precious artifact of all, worthy of preservation at any cost. We can bring this dizzying speculation down to earth with a simple analogy from our own experience with disaster preparedness. We build levees to hold back floodwaters, we engineer buildings with flexible frames to withstand earthquakes, and we create vaccines to preemptively arm our bodies against viruses. These are all forms of local environmental stabilization. The dream of a quantum anchor or a constant stabilizing field is simply this same principle scaled up to the universal level. It is the ultimate expression of the engineering impulse to not just live within our environment, but to actively maintain and repair it, even when that environment is space-time itself. It reflects a desire to move from being passive inhabitants of the universe to becoming its active stewards, with all the terrifying responsibility that entails. For humanity in its current infancy, such technologies are far beyond our grasp, but the thought experiment forces us to consider our own, more immediate long-term survival strategies. If we cannot stop a collapse, could we hope to outrun it? This is the impetus behind multi-planetary and eventually multi-stellar colonization. By spreading beyond Earth and then beyond the solar system, we wouldn't be avoiding the collapse but rather hedging our bets. A failure of physics would likely be universal, but if it propagated at the speed of causality, the speed of light, a civilization with a sufficient head start could, in theory, stay ahead of the wave of dissolution. Colony ships traveling at a significant fraction of light speed could race ahead of the changing laws, buying precious time to perhaps understand the phenomenon or find a refuge. It would be a desperate galactic exodus, a running battle against the unraveling of reality itself. An even more radical form of preservation involves not our biological bodies, but our consciousness and culture. The concept of a digital backup takes on a profoundly new meaning here. It wouldn't be enough to save our art, history, and knowledge on a hard drive. That drive itself would be subject to the changing physics. Instead, a civilization might seek to encode the essential information of its existence, the mathematical descriptions of its physics, the genetic code of its biology, the totality of its accumulated wisdom into a format that is immune to the collapse. This could mean converting that information into a substrate based on a more fundamental, perhaps quantum gravitational level of reality, or even printing it onto the fabric of spacetime itself, like a cosmic message in a bottle meant for whatever or whoever might come after. The goal would be to ensure that even if the universe forgets the rules, a record of what those rules once were and what they made possible might somehow survive. These strategies, from cosmic engineering to interstellar flight to informational salvation, are not about winning a fight against the silent collapse. They are about the profound, unyielding human drive to leave a mark, to ensure that even in the face of total annihilation, our story, or the story of the reality that allowed us to exist, is not utterly and completely erased. But the true, existential dread of a silent collapse isn't found in the failure of a single, isolated law. The universe is not a collection of independent rules operating in a vacuum. It is the ultimate complex system, a deeply interconnected and exquisitely balanced web where each thread supports and is supported by countless others. A failure in one fundamental force would not be a solitary event. It would trigger a catastrophic domino effect, a cascading chain reaction of systemic collapse that would race through every level of reality, from the quantum to the cosmic, unraveling the entire tapestry of existence in a horrifyingly short amount of time. This is the ripple effect where the silent collapse becomes a deafening roar. To understand this, we can turn to the insights of complexity science, a field dedicated to studying how the components of a system give rise to its collective behavior. Melanie Mitchell, a professor at the Santa Fe Institute and a leading expert on complex systems, often explains that a hallmark of such systems is emergence, where the whole is greater than the sum of its parts, exhibiting behaviors that cannot be predicted by studying any single component in isolation. The universe is the most complex system we know, and its stable, predictable behavior is an emergent property of all its physical laws working in concert. Crucially, Mitchell and her colleagues study how systems can exhibit cascading failures, where a single, localized breakdown can propagate through the network, causing the entire structure to collapse. This is exactly what would happen if a physical law failed. The universe's laws are not just connected, they are codependent. The strong nuclear force holds atoms together, but it is electromagnetism that governs how those atoms interact to form molecules. Chemistry is entirely built upon the electromagnetic force. If electromagnetism were to weaken, the intricate dance of electrons that forms chemical bonds would fall apart. Molecules would simply dissociate, turning a living cell into a disorganized soup of individual atoms. But the collapse wouldn't stop there. Biology is applied chemistry. The failure of chemistry means the immediate end of every biological process: respiration, neural signaling, DNA replication. All of it would cease in an instant. A failure in physics doesn't just break the rules of the game, it dissolves the game board and all the players upon it. This terrifying domino effect would not be limited to our planet. It would echo across the cosmos in a chain reaction of staggering scale. Imagine a single, seemingly minor change. The strength of the strong nuclear force increases by a fraction of a percent. This small tweak at the quantum scale would have immediate and devastating consequences. Inside every star, the rate of nuclear fusion would skyrocket. Stars that were once stable for billions of years would now burn through their fuel in a frantic, furious rush. The universe would be lit up with a wave of premature supernova as stars across galaxies exploded in a synchronized firestorm of death. But the chaos is just beginning. These supernovae are the universe's primary forge for heavy elements like iron, carbon, and oxygen. A changed fusion process would create a different, and likely far less useful, set of elements. The cosmic abundance of life-essential atoms would be altered, potentially leaving the universe barren of the building blocks for rocky planets and life. The initial ripple, a tiny change in a nuclear constant, would cascade upward through increasing scales of complexity, from altered stellar physics to a changed interstellar medium, to a complete rewrite of planetary formation and chemistry. The universe might not be torn apart. It might instead be homogenized, simplified into a boring, sterile state of hydrogen, helium, and a few other simple elements, its potential for complexity permanently erased. This forces us to confront the ultimate, haunting question that hangs over the entire concept of a silent collapse. In the face of such a total systemic breakdown, would the universe ever find a new equilibrium? Or would it simply spiral into an irreversible descent toward nothingness? The answer likely depends on which law fails and how. Some changes might lead to a new, stable, but horrifyingly barren state, a universe that is cold, simple, and forever inert. Other changes could be so profoundly destabilizing that they would trigger a feedback loop of destruction. For instance, if the failure of one law somehow altered the value of the cosmological constant governing dark energy, it could cause the accelerating expansion of the universe to become vastly more violent. This could lead to a Big Rip scenario, but one that is triggered internally by a law's failure rather than by the natural evolution of the cosmos. In this case, the dominoes wouldn't just fall, they would annihilate each other upon impact, ensuring no new structure could ever form again. The silent collapse would be the universe's final act, a suicide initiated by a single, broken rule, leaving behind only a formless, lifeless void where the magnificent complexity of galaxies, stars, and conscious life was nothing more than a fleeting, forgotten possibility in the dark. Yet as we contemplate the terrifying possibility of our universe's rules failing, a profound and almost comforting idea emerges from the edges of theoretical physics, the multiverse. This is the breathtaking hypothesis that our cosmos, with its specific, life-permitting laws, might not be the only one. Instead, it could be just a single bubble in a vast, frothing cosmic ocean, one bubble among an infinite number, each with its own unique and perhaps wildly different set of physical constants. In this staggering vista, a silent collapse in our local reality would not necessarily be the ultimate end of everything. It could be a tragically local event, a single bubble popping in an endless sea of universes, leaving the wider multiverse utterly untouched and teeming with possibilities. This concept finds one of its strongest foundations in the theory of eternal inflation, pioneered by physicists like Alan Guth. His work on the inflationary model suggests that in the very first moments after the Big Bang, space-time underwent a period of exponentially rapid expansion. Guth's key insight was that this inflation might not have stopped everywhere at once. Instead, it could be eternal, with the fabric of space-time continuing to inflate at an incredible rate overall, while in certain pockets, this inflation slows or stops, allowing a hot, dense Big Bang to occur and a universe like our own to form. Each of these pockets becomes a separate bubble universe, forever isolated from the others by the ever-expanding inflationary space between them. As Guth himself has described it, it's like a constantly rising loaf of raisin bread, where each raisin is a separate universe, forever moving apart from all the others as the dough expands. In this model, the fundamental constants, the strength of gravity, the mass of an electron, could be set randomly within each bubble during its formation. Some universes might have laws where gravity is so strong they instantly collapse into black holes. Others might have forces so weak that no atoms can ever form. And a precious few, by pure statistical chance, would have the perfect Goldilocks balance that allows for stars, planets, and life. Our existence here is not a miracle. It is a coincidence made inevitable by the sheer, infinite number of tries. To make sense of this almost ungraspable idea, we can use a powerful metaphor. Imagine reality is not a single house, but an infinite mansion with an endless number of rooms. Our universe is just one room in this mansion, furnished with our specific laws of physics, a chair that always remains solid, a light switch that always works, gravity that always pulls down. Now imagine the silent collapse begins in our room. The chair loses its solidity, the light switch does nothing, gravity reverses. It is the end of our world. But on the other side of the door, in the next room of the infinite mansion, the chair is still solid, the light still turns on, and gravity still functions perfectly. The rules are simply different there. The collapse is contained. The horror is real for us, but it is not universal. The mansion, in its entirety, remains standing. This metaphor allows us to hold two terrifying ideas in our minds at once: the absolute catastrophe of our local reality failing, and the profound, cosmic-scale relief that it might not be the final word on existence. This leads to one of the most compelling and ethically fraught thought experiments in all of science. If a silent collapse were imminent in our universe, and if we somehow developed the technology to tear open a doorway to another bubble universe, one with stable, life-friendly laws, what would we be? Would we be desperate refugees fleeing a doomed world in search of sanctuary, grateful for any corner of reality that could sustain us? Or would we, in crossing that boundary, become invaders? Our very presence in a new universe could be an act of contamination. We would bring with us not just our culture and our biology, but the underlying quantum information of our home dimension, potentially introducing instability into a pristine cosmos. The act of crossing over might itself be violent, requiring energy so immense that we could inadvertently damage or even pop the bubble we are trying to enter. The ethics are a nightmare. Do we have the right to seek salvation if it risks destroying another world, even an apparently empty one? Or does the imperative to survive our own extinction override all other considerations? This is no longer the plot of a science fiction movie. It is a serious moral dilemma that emerges directly from our most advanced cosmological theories, forcing us to confront what responsibility comes with the audacious dream of multiverse travel. Ultimately, the multiverse hypothesis transforms the silent collapse from a universal apocalypse into a profoundly personal tragedy. It offers a form of cosmic solace, the idea that existence itself is resilient even if our particular corner of it is not. Life and consciousness might continue in a billion other bubbles, unaware of our fate, but it is a cold comfort. It does not save us. It simply redefines our impending loss, not as the end of everything, but as the end of our specific everything, our stars, our history, our unique window into reality. The possibility of other universes does not diminish the precious, fragile beauty of our own. It magnifies it. We are not inhabitants of a generic universe, but of a very specific one with very specific rules that allowed us to emerge and to gaze in wonder at the stars, and to even conceive of the multiverse beyond them. The silent collapse, even if isolated, would forever erase that particular flavor of wonder from the cosmos. It would be the closing of a door to one room in the infinite mansion, a room that contained something truly priceless, us. Yet as we stand before the abyss of a silent collapse, a deeply human question rises above the scientific and philosophical chaos, one that forces us to examine our own conscience and the very structure of our global society. In the face of a universal catastrophe, would the suffering be distributed equally? Or would the deep, pre-existing inequalities that already define our world determine who gets a fighting chance and who is simply erased? The terrifying truth is that while the collapse of physics itself would be utterly democratic, striking every atom on Earth with impartial fury, the human experience of that collapse would be anything but. Our ability to comprehend, respond, and potentially mitigate the immediate effects would be entirely dictated by the accident of our geography and our access to technology and knowledge, creating a horrifying hierarchy of suffering in the final moments of civilization. On the surface, it's tempting to believe that a failure of fundamental law would be the ultimate equalizer, a catastrophe so absolute that it would instantly render all human-made distinctions of wealth, power, and nationality meaningless. In the first seconds of the event, a billionaire in a fortified skyscraper and a subsistence farmer in a remote village would indeed face the same physical reality, the same disintegrating matter, the same failing light, the same unraveling biology. The universe's new, chaotic rules would not check your bank balance before allowing gravity to reverse for you. In this raw, physical sense, the collapse is the most impartial disaster imaginable. But this is a cold, superficial comfort. The human response, the capacity for understanding, preparation, and resilience, is where this thin veneer of equality shatters. Advanced technological societies, with their dense networks of scientists, engineers, and centralized infrastructure, would have one critical, fleeting advantage: the capacity to recognize what is happening. A neutrino detector buried deep underground or an orbital observatory might pick up the anomalous data seconds or minutes before the effects became macroscopic, triggering alerts through hardened government and military networks. This wouldn't be enough to stop the collapse, but it might be enough for a privileged few to understand the terrifying truth in their final moments, to hear a warning and perhaps even initiate a desperate, last-ditch contingency plan. For the vast majority of humanity, particularly in regions with less technological saturation, the collapse would arrive without context or explanation, a sudden, inexplicable, and absolute descent into a nightmare where the world itself has gone mad. The suffering would be compounded by a profound, isolating confusion, a terror made worse by the complete absence of any framework to understand it. This disparity in knowledge and preparedness mirrors a chilling ethical dilemma we are already grappling with today on a smaller scale: the unequal impact of climate change. The nations and communities that have contributed the least to global carbon emissions are often the most vulnerable to its devastating consequences: rising sea levels, extreme weather, and agricultural failure. They lack the vast financial resources, the advanced infrastructure, and the technological buffers that wealthier nations can deploy for adaptation and disaster response. A silent collapse would be this injustice multiplied to infinity. A society with decentralized renewable energy grids, advanced material science labs, and deep underground facilities might, for a few extra hours or days, maintain a bubble of relative stability, a desperate attempt to run experiments or preserve knowledge. Meanwhile, a developing nation reliant on imported technology and centralized power systems would face immediate and total blackout, its people left with no information, no coordinated response, and no refuge from the chaos. The collapse would not create this inequality. It would ruthlessly exploit and exacerbate the inequalities we have already built into our world, turning existing gaps in wealth and technology into unbridgeable chasms between a moment of confused terror and an eternity of silent nothingness. The philosophical framework for analyzing this terrifying equity crisis can be found in the work of ethicists like Peter Singer and his principles of distributive justice. Singer argues that we have a moral obligation to help those in severe need, and that this obligation extends globally, not just to our immediate neighbors. His famous drowning child thought experiment asks why we would feel compelled to save a child we see drowning in a pond in front of us, yet feel little obligation to save a child dying of poverty in a distant country, even though the cost might be the same. In the context of a silent collapse, this analogy becomes horrifically literal. The advanced nations of the world, who possess the majority of the scientific knowledge and technological tools that could, in theory, be used for a coordinated global response, have a profound ethical responsibility. But could that responsibility ever be fulfilled? The very nature of the collapse would make large-scale international aid impossible. There would be no time to send resources, no way to communicate a plan, no means of transporting people to safety. The obligation would shift from active rescue to a tragic, passive question: how did we use our advantages in the time before the collapse? Did we hoard knowledge and technology, or did we work to globally disseminate scientific understanding and build resilient infrastructures worldwide? The bitter irony is that our failure to adequately address distributive justice in smaller, manageable crises like climate change or pandemic preparedness is the clearest predictor that we would fail spectacularly in the ultimate crisis. Our inability to share vaccines equitably during a global pandemic is a stark preview of our inability to share survival strategies during the end of the world. This forces a deeply personal and uncomfortable reflection on the balance between preparedness and fairness. Is it ethical for a society or even an individual to invest immense resources in preparing for a low-probability, high-impact event like a silent collapse when those same resources could alleviate known, ongoing suffering for millions today? Building hardened bunkers, funding exotic physics research into existential risks, or stockpiling resources for a select few could be seen as the ultimate act of selfishness, a retreat from our collective responsibilities into a private fortress. Conversely, one could argue that it is a rational, if grim, form of insurance for the continuity of knowledge and perhaps even humanity itself, a way to ensure that even if the vast majority are lost, a spark of consciousness and understanding might survive to eventually reclaim a broken world. There is no easy answer here, only a tragic trade-off. Investing in universal education, poverty reduction, and global health equity doesn't directly prepare us for a physics collapse, but it does create a more robust, knowledgeable, and cooperative global society that would be better equipped to face any crisis, known or unknown. Perhaps the most ethical form of preparation for an unimaginable catastrophe is not to build a private ark, but to work toward a world where everyone has a place on the deck, a world so fundamentally fair and resilient that even in the face of ultimate ruin, the gap between who suffers first and who suffers last is measured in moments of shared understanding rather than in lifetimes. Entrenched inequality. Yet even in the face of such total systemic dissolution, the human spirit is wired for a stubborn, almost irrational hope. The hope that somehow, against all odds, a remnant might persist, not just to survive, but to find a way to thrive within the chaos. This isn't a hope for a return to normalcy, but for a transformation so profound that it redefines what it means to be human. Imagine a scenario where the collapse is not instantaneous, but a slow creep, a gradual rewriting of physical laws over generations. In this long twilight, a small, isolated community of survivors, perhaps in a deeply shielded bunker or on a generation ship already en route to another star, finds that their reality is steadily becoming alien. The first generation would be the physicists, the engineers, those who remember the old rules. They would watch in horror as their most fundamental equations began to fail, their instruments returning nonsense. Their greatest achievement would be one of desperate documentation, creating a record of the great unraveling, a Rosetta Stone mapping the dying laws of the old universe to the emerging, chaotic principles of the new. They would be the last guardians of a lost world, teaching their children concepts that were becoming less true with every passing day. The next generation, however, would be the true adapters. Born into a world where light might not always travel in straight lines or where gravity was a weak and sporadic suggestion, their developing brains would wire themselves to this new normal. Their intuition would be fundamentally different from ours. Where we see a solid wall, they might perceive a temporary confluence of particles, a semi-stable pattern in a fluid reality. Their greatest achievement would be the birth of a new science, one not based on predictable constants but on probabilistic fields and contextual interactions. They wouldn't ask, what is the law of gravity, but what is the probability that this mass will attract that mass at this specific moment, given the current local state of the gravitational field? Their mathematics would be wildly different, perhaps based on non-linear, multi-valued logic that could handle a universe of fleeting truths and conditional realities. They would learn to navigate their world not by following fixed rules, but by sensing the ever-shifting currents of a fundamentally fluid existence. This path of adaptation inevitably leads us to the most radical speculation of all, the transition from a biological to a post-physical existence. If the physical substrate of the universe is no longer reliable, perhaps consciousness must divorce itself from it entirely. This is the realm of transhumanist thought, famously championed by futurists like Ray Kurzweil. He speaks of a coming singularity, a point where technological progress becomes so rapid that it leads to a fundamental transformation of human life, including the potential to upload our consciousness onto a more durable digital substrate. In the context of a silent collapse, this wouldn't be a choice for transcendence, but a desperate necessity for preservation. If atoms can no longer be trusted to hold together, perhaps we could encode the pattern of our minds onto a more stable medium, something not subject to the failing forces of our dimension. This new existence would be incomprehensible to us. As science fiction legend Arthur C. Clarke's third law states, any sufficiently advanced technology is indistinguishable from magic. A consciousness that has escaped its biological cage and learned to manipulate the very code of a broken reality would appear as pure magic, or perhaps as a new form of deity, its capabilities limited only by the new, strange rules of the cosmos it now inhabits. This forces upon us a final, deeply poignant question about the meaning of legacy. In a universe that has forgotten its own rules, what would stand as humanity's greatest and most enduring achievement? Would it be the mere fact of our survival, the stubborn persistence of a flicker of consciousness in an overwhelming darkness? This in itself would be a monumental feat, a testament to an indomitable will to exist. Or would it be our incredible capacity for adaptation, our ability to not just endure but to learn, to build a new understanding from the ashes of the old? To become natives of a reality that would strike us as a nightmare, to forge a new culture, a new art, a new way of being from the raw, chaotic material of a broken physics. Yet perhaps the most profound achievement would be neither survival nor adaptation, but the relentless pursuit of understanding itself, even in the midst of the collapse, to never stop asking why, to never cease trying to decipher the new logic of the cosmos, even if that logic is madness. This relentless curiosity is the purest expression of our humanity. It would be the ultimate declaration that even if the universe changes all the rules, the human drive to comprehend it remains, our final and most beautiful rebellion against the silent, indifferent dark. And so we find ourselves at the end of this journey, having stared into the abyss of a universe without rules. We've traveled from the silent, quantum unraveling of atoms to the cosmic scale disintegration of galaxies, and witnessed the terrifying fragility of everything we have ever known. This thought experiment is far more than a fanciful exploration of physics. It is a profound meditation on the nature of reality itself, revealing just how precariously our existence is balanced upon a set of constants we did not choose and cannot control. We have seen that a betrayal by gravity would not merely make us float away, but would tear our planet apart and silence the stars. A failure of electromagnetism would erase the very concept of solidity, dissolving our bodies and our world into a formless mist. The unraveling of thermodynamics would shatter time's arrow, leaving our memories and our future in a tangled, meaningless knot. Each potential collapse is a door to a different kind of oblivion, reminding us that the cosmos is not obligated to make sense to us or to allow for our continued presence within it. This journey forces us to confront the most fundamental questions about our place in the universe. Are the laws of physics discovered universal truths, or are they merely temporary, local ordinances in a multiverse of infinite possibilities? Is our reality a fixed stage, or is it a fragile construct, a delicate equilibrium that could be upset at any moment? The silent collapse challenges the very core of scientific inquiry, suggesting that our hard-won knowledge could be rendered obsolete by a universe that decides to change the rules of the game. It humbles us, stripping away our technological arrogance and revealing that for all our engineering marvels and intellectual triumphs, we are ultimately guests in a house whose foundations we did not lay and whose stability we must simply hope endures. In the face of such staggering implications, the words of the late, great astronomer Carl Sagan ring out with a new and powerful resonance. He famously said, "The cosmos is within us, we are made of star stuff." This is not just a beautiful metaphor, it is a literal, scientific truth. The carbon in our cells, the iron in our blood, the oxygen we breathe, all of it was forged in the nuclear furnaces of long-dead stars and scattered across the galaxy by ancient supernova explosions. We are not just inhabitants of the universe, we are a physical part of it, a conscious expression of its own matter and energy. This profound connection makes the silent collapse not some distant, abstract tragedy, but a deeply personal one. It is the story of the universe potentially turning against itself, of the star stuff becoming aware of its own exquisite fragility. This realization should not fill us with despair, but with a profound sense of wonder and responsibility, a desire to protect and understand the miraculous, delicate balance that allows us to be here, to think, and to wonder at it all. Now we turn the question over to you. After this journey through cosmic vulnerability, which law's failure unsettles you the most? Is it the intimate horror of your own body dissolving with the strong nuclear force, or the existential dread of a universe where time itself has no meaning? Share your thoughts in the comments below. We are endlessly fascinated by these discussions. If you found this exploration of reality's razor's edge as captivating as we did, please show your support by liking this video and subscribing to the channel. Tap the bell to ensure you don't miss our next deep dive into the universe's greatest mysteries, where we continue to explore the wonders and the terrors hidden in the fabric of the cosmos. Thank you for joining us on this journey to the edge